In this video, we are going to learn about the word embeddings. So as we proceed in this video, we will understand what exactly is this word embeddings, why is it relevant for natural language processing, and I'll also show you a demonstration about the word embedding in a visual manner so that you clearly understand how it actually look like and why it is relevant for us and how it is beneficial for us, which will pave as a foundation for you to learn in depth as we proceed in this section. So let's get started. Now, when I say word embedding, so word embedding in natural language processing is an important term, and this is actually used to represent the words for textual analysis. So we use this word embeddings to represent the documents and the word in my corpus. This will help me to represent the text data in a numerical format, and this numerical format is a real valued vector. Now, this word embedding is one of the advancement that we had in natural language processing. So this has actually improved the ability of my computers as well as my machine learning models to understand the text data in a much more effective way compared to the other methods. Now, I can say that this method of representing the text data, especially with the help of word embeddings, has been considered one of the most significant breakthrough that we had in deep learning. And even the advanced models such as the transformers, we actually use the word embeddings as a way to represent my individual words. Now, what we do is in this overall approach of word embeddings, we are going to have the words and documents represented in the format of a numeric vectors. And along with that, I'll also ensure that while representing these text data, so the similar words will have the similar vector representation. So the words with a similar meaning will have the similar representation. The extracted features which I get out of this word embedding, it will be then fed into my machine learning model so that the text data that I have, it will have the important elements from the overall text. The numerical representation will clearly represent the text data that we are working with, which ensures that we have captured the semantic as well as the syntactic information. Now, another best part is using this embedding, we can approximate the meaning of a text word and represent it in a low dimensional space. Now, this low dimensional space is not dependent on the number of words that I've got in my vocabulary, which was the scenario of term frequency or TF-IDF technique. Okay, now because of the popularity of NLP as well as the pace in which the technology is moving forward. So word embedding is one of the very important topic when it comes to natural language processing. And we'll be learning in detail as we progress in this section. So in practice, whenever we are working with the word embeddings, so we generally make use of the pre-trained word embeddings. So we have got various pre-trained word embedding models like Flare, FastText, Spacey, and other libraries that we have got with us. So we generally use this pre-trained word embedding models to generate the textual data in a numerical format, and this numerical format data will ensure that it will also consider its meaning as well. So this is the core concept behind this word embedding technique. Now, to help you understand this overall concept of word embedding and how it is being used, let's take up a use case. So we've got a problem statement which is about the tweet classification. Let's say you have been given a supervised learning task and you have to analyze the tweets, and these tweets are about the real disasters that is happening, and you have to classify them whether the tweet is about the real disaster or not. So which means given the text data, you have to classify to one of the classes like the real or fake. Now this is a simple task of text classification. Now, in order to do this task of text classification, this text that I have got over here, this will be my independent term. So independent term is nothing but the input value. And the label that I have got, this will be my dependent term. So I'm interested in establishing the relationship between this independent term as well as the dependent term. Now, in order to understand this relationship in an effective manner, you have decided that you will make use of the machine learning model. But one key challenge and the expectation from this machine learning model is this model expects the data in the format of a numerical format. Now, the question is, which method can I use? Well, in this time, what we can use is we can make use of word embeddings to represent this text data in a numerical format. The reason that I would prefer to work with word embeddings because this numerical representation of the text, it will ensure that it will capture the words that are similar together and it will have the similar vector representation. So as a result of this, we can use the word embeddings to represent the individual words as real valued vectors in a lower dimensional space and capture the interword semantics, and all the text data will be represented with the help of fixed length vectors. And that is how the usage of word embeddings comes into picture when we are talking about the task of natural language processing task, that is classification. Okay, so that's how the word embeddings would fit in. Now that you have understood about the word embeddings and its usage, so let's get a clear idea about this word embeddings and how it actually look like. So as I mentioned, when we talk about this word embeddings, so here in this topic of word embeddings, so it's all about representing the text data in a numerical format. Now by having the data represented in a numerical format, here we have got a lot of advantages. So this is a link. I'll share those links in the description as well so that you can also try out. So here, this contains the pre-trained model. There are various pre-trained word embeddings model that are available right now. So one such model that I have considered is English Google News negative 300. So this is a pre-trained word embedding model that I have considered. Now, one thing that I've highlighted is the word embeddings capture the meaning and it will ensure that the word which are similar to the word that I'm interested in, it will have the similar vector representation. Now to help you understand the same, here I have input the word as king, and when I say show nearest and select as 10, it is going to show me as what are the top 10 vectors which are having the same vector scores as the word of the king. So it says king is similar to kings, queen, monarch, crown prince, prince, sultan, ruler, princess, throne, and royal. So the vector representation of these words are similar to the vector representation of the word king. Now I'll take one more example. Let's say New York. Okay, I'll take the input as New York, and if I say show nearest, so the vector representation of the word New York is very similar to Manhattan, NY, Brooklyn, Long Island, NYC, Upstate, New Jersey, Bronx. So the words which are similar to the New York are actually having the similar vector representation. So what it means is I'm actually capturing the words which has the similar meaning has the similar vector representation. Finally, I'll take one more word. Let's say joy. So joy is a word that I'm going to consider, and if I look into the top 10 nearest words, sheer joy, exhilaration, joyful, delight, excitement, thrill, happiness, joyous, jubilation. See, the words which have got the similar meaning as joy has got the similar vector representation. So, in the task of natural language processing, suppose if I come across a word which is not present in my vocabulary, I can make use of the word embedding and I can get its vector representation. So that's a benefit of the word embedding. So even though it may not be present in my training data, I can get its similar words or I can get its representation from the pre-trained word embedding. Okay, and apart from these, since we have got the vector which captures the meaning, so I can calculate the similarity between the words. I can say king and queen, it has got the similarity score as 0.65. Now when I say king and prince, so if I say a similarity, there's a similarity score as 0.61. And when I say king and man, I've got the similarity score as 0.22. So I can get the similarity scores as per my requirement. So for example, when I say USA and if I say New York, If I show a similarity, so I can get its similarity, how similar those two words are. And not just that, we can also perform the task of analogy. So it says India to Delhi, what is China to dash? So if I click on show, it says China to, in the top two result, I can see the outcome as Shanghai. So you can clearly observe how effective the word embeddings are. It is clearly able to capture how a particular word is being used. Now, this is another page which describes about how we actually train the word to vec model, which is the model which we'll be learning in the future sessions. So when we talk about this word to vec model is nothing but word to vector representation. Here I've got the text. Now, whenever we are training this word to vec model, there are actually two types of word to vec model. One is continuous bag of words technique and the skipgram technique. We can either choose any of the technique as per our preference, and then we will specify the window size and we'll generate the data. Once we generate the data, we'll simply go ahead and train the model just like we would train any other neural network. And once I've done that, I can now get the vector representation of the individual words and see how each of these words are represented with the help of word embedding. So this is the core intuition behind this word embeddings, which we'll be learning as we progress in the learning journey. So to summarize, when I say word embedding is the vector representation of the words, which also considers as how a particular word is being used. Now, with this advantage, the words which has got the similar meaning will have the higher similarity score. The words which has got the dissimilar meaning will have the lowest similarity score. Okay, so that's the main advantage of using this word embeddings. So if I want to give some more information about this word to vec, so word to vec is a model which is developed by the researchers at Google in the year of 2013. And this word to vec model is based on distributional hypothesis. And as you have seen earlier, so in the scenario of this word embedding, there are actually two variants of word to vec model. One is continuous bag of words technique, and the other technique is called as a skipgram technique. So we will discuss and learn more about these two variants of word to vec model as we progress in the next video. So in the next video, let's understand the continuous bag of words technique, which we use it to generate the word to vec. So I'll see you in the next video where we'll discuss about this technique. In the last video, we had an introduction to word embedding. Now, as we proceed in this video, we are going to understand the intuition behind this vector representation and what are the benefits that we are going to enjoy if we represent the given text data in a numerical format. So, when I talk about the vector representation is nothing but representing our string or a text data in a numerical format which has got a fixed length vector. And in the fixed length vector, each and every element is made up of numerical values. Now that's the core idea behind this vector representation. And we follow this vector representation even in the scenario of this word to vec model. Now this word to vec model is an approach that has been shared by the team of Google for creating the word embeddings. And this word embeddings is one of the most fascinating ideas in the natural language processing. Now, if you have used Siri, Google Assistant, Alexa, Google Translate, or even any of the applications in your mobile app which predicts the next thing, then the chances are you have benefited a lot from this overall approach that has been shared by the Google in the year of 2013. And the best part is the recent advancements in natural language processing. So all these were actually being able to do by having this vector representation, that is word to vec ideas as a foundation. So that is the importance of word embedding. Now let's try to analyze, okay, why this vector representation is really required. Now let's take up an example. Okay, this time I'm going to take an example. Let's say I've got the set of learners with me. Okay, I've got a student 1 and I've got student 2 and I've got student 3 and I've got the student 4. So I've got 4 students information with me, and along with their student IDs, I have the marks that has been secured or the percentages secured by the individual students in the 10th standard or the class 10 or the class 12. Okay, this is the percentage scored in the class 10 and the class 12. So student 1 has secured the 90% in the class 10, and the student 1 has secured, let's say, 55% in the class 12. Now student 2 has secured, I would say, 90% in class 10, and student 2 has secured actually 92% in class 12. And student 3, he has secured 35% in class 10, and in class 12 he has secured 85%. And student 4, he has secured 89% in class 10, and he has secured 95% in class 12. Now if I give you this data to you, and if I ask you as, tell me which of the students are closer together and which of them are actually performing really well, then you have to think about it. You have to analyze each and every percentage value and then decide, okay, so which students are actually similar together. Now that's a very manual task, isn't it? But what if I tell you there's a mathematical way? The mathematical way, more specifically, will make use of the linear algebra way. So what I'm going to do is, I'm going to represent the individual student score in the format of a vector. So my student 1, I'm going to represent it in terms of grades between 0 to 10. So 90 means I'll say it as 9.0 and 5.5. And student 2 vector, I'll represent it as 9.0 and 9.2. And student 3, I'm going to represent it with the values as 3.5 and 8.5. Now I'll mention the student 4 as a vector representation of 8.9 and 9.5. So this is how I'll be representing my individual student score in the format of a vector. Now you might ask me, what's so big deal if I have the data in the format of a vector? Well, let me come to that big deal. So what I'll do is, I'm going to represent these vectors in a two-dimensional plane. So let's go ahead and do that. So first student 9.0 and 5.5. So here I'm going to say 9.0 comma 5.5. Okay, so let's go ahead and add a point over here. Okay, so the point is, in this example, so it is 9.0 and 5.5. So here I'm going to write it like this, 9.0 and 5.5. It will come somewhere over here. So I'm going to place a point, assuming that my x-axis as 9 and 5.5, I'll place it somewhere over here. So this is my student A or the student 1. So 9.0 comma 5.5. Okay, so this is my student 1. Next, I'll go ahead and I'll add the another student's point over here. The another student is 9.0 and 9.2. So I'm going to say B is equal to 9 comma 9.2. Okay, next I'll say C is equal to, this is another student, and his scores will be 3.5 and 8.5. So 3.5 and 8.5. Okay, and finally my student D, that is the student 4, is 8.9 comma 9.5. So I'll say D is equal to 8.9 comma 9.5. Okay, so what I have done is I have represented the individual student score as the points in the plane. Now I'm going to join these data points from the origin. So I'm just going to join these data points. I'll write it like this. Okay, so I'm going to mention it in this way. So here, yeah, this is one vector, this is another vector, and this is vector D. And let's have a look into the point C, 3.5 comma 8.5. So let's go ahead and check where exactly it is present. Okay, yeah, so this is where the data point is. So I'll just go ahead and join it as a vector. So by drawing a vector, so it's pretty much clear that these two data points, point D and point B, they are actually closer together. See, point D and point B are closer together. And which means that these two students are having the similar scores. The another way that I can represent the similarity when I have the data in the format of a vector is I can make use of cosine similarity. So for a given set of student vectors like this, I can compute the cosine similarity between them. If I compute the cosine similarity between them, I can compute whether these two student score is actually similar or not. And if required, I can also measure the distance between the vectors as well. So I can find the distance between one vector to another vector, and I can measure, okay, how different these two vectors are. So I can do all this sort of mathematical analysis if I have the data represented in the format of a vector. Now in this example, I've got the information about a specific student from the class course of class 10 and class 12. Now, if I want to learn more about the student's performance in the academics overall, then at that time, obviously, I would require more information about him. Maybe I need the information about his graduation. I will be requiring the information about his post-graduation. And after the post-graduation, maybe if he has got any work experience, I have to note down those as well. And for that, I have to represent those values in a numerical format. If I have all the values represented in a numerical format, then at that time, instead of having a vector in two-dimensional space, I can have a vector in n-dimensional space. If I have a vector in n-dimensional space, the concept still is valid. That means I can still go ahead and find the similarity between those vectors to check how each and every individual student is similar together or not. So that is one of the key thing when we are representing the data in the format of a numerical format, that is vector format. Now in this word to vec representation, I'll be interested in representing the words in a vector format. And while representing the text in a vector format, it will also consider how a particular word is being used. And that is what we call it as a context. By considering the context, I'm going to have a numerical representation so that I can perform the required mathematical operation between those word representation. Here, in order to learn the context, we make use of a technique that's called as language modeling technique. Now, when I say language modeling technique, a language model is basically a probability distribution over the words or word sequences. Normally, if you think about the applications, let's say a transfer learning application, we are going to make use of a pre-trained model, and using the pre-trained model, we are going to implement it for the fine-tuning a task. Now, in the scenario of natural language processing, for the task of this language modeling, I'm going to get an entire Wikipedia corpus. I'm just giving you an example. I'll take an entire Wikipedia corpus. So what I'll do is I'll split this entire sentence into the pair of words. To give you an example, suppose if I go to the data science Wikipedia, and if I go to this page, so this is the Wikipedia page of a data science would look like. Now, the way that I'll be performing this language modeling is I'm going to perform the tokenization on this entire text corpus, and I'm going to do a training like this. With the current word, what will be the next word? With my current word, what will be the next word? With my current word, what will be the next word? So like this, I'm going to build a model. and I'll train it on a very humongous corpus. So at the end, whatever the model that I'll be training, that has learned the overall context in which the word has to be represented. So that is the core principle behind this language modeling technique. Now, when I say word embedding is a embedding matrix that we are going to generate as a result of performing this activity of language modeling. Now, in order to perform this language modeling on a text data, we have actually two methods. One is continuous bag of words method, and the other method is called as skipgram method. So we can use either of these approaches in order to prepare the model, which is a language modeling model. And once I've got the language model, I can then go ahead and use the text representation for the future task. So that text representation is what we call it as a word embedding vector. Okay, so that's the core principle behind this word embedding. I wanted to spend some time and explain you on this concept because this is very important. Having this basic idea will help you a very long way in this section, because this section is very important from the NLP practitioner perspective. So if you've got any question, please let me know in the Q&A section. So as we progress in our learning journey, in the next video, we are going to learn about the word embedding with pre-trained models. So I'll see you next time. Hey everyone, welcome back to your learning journey. Now in the last video, you have understood the importance of word embeddings. Now as we progress in this video, we are going to play around with this pre-trained word model, and we are going to look into its vocabulary, and also we'll try out some of the basic operations whenever we are working with this word vectors. Okay, so let's get started. Now as I've specified in the last video, this word embeddings is based on the research paper, that is Word to Vec research paper. The research paper is Word to Vec research paper. Now, this was on the basis of the research paper submitted by the Google team in the year of 2013. Now, when they have actually performed this research and submitted this research paper, the authors, they have also released a large word to vec model, which they have actually trained on 100 billion words from the Google News data set. That means they have trained this entire word to vector model from the 100 billion words. Okay, it's actually 100 billion words, and this has been trained from Google News data set. Now, what this contains? This model contains 3 million words. That means in the vocabulary, it contains 3 million words, and each word has 300 features. So with this, you can clearly observe the size of the features is not dependent on number of words. In this word-to-vec model, even though I've got 3 million words, I just have only 300 features representing my individual word. Okay, so this is the best model that we have got from the word to vec perspective. Now I've got a cell. This is a cell. Once I execute this cell, this is going to download the model file to my Google Colab instance. Now, along with downloading this pre-trained model, I'm also going to load the package that is called as Gensim. Now, Gensim is a package which implements all the basic features that I would need in order to load this word-to-vec model. That is like loading this word-to-vec model and accessing the vocabulary of this word-to-vec model. And also, if I want to perform any similarity operation, then in all those scenarios, I can make use of this Gensim package. Okay, so I'll begin by importing this Gensim package. So I'm going to say import Gensim. Now, apart from this import, so here when I download this model, so this model is in the compressed format. Now, with this compressed format, it is around the size of 1.66 GB. So that's the size of this model. Now, what I'm going to do is I'm going to uncompress it. So if I do this uncompression, so currently it is in gz format. So if I want to do the uncompression, so I'll say gun zip and I'll mention the file name. So this is the file name that I've got. Now, once I execute this, this is going to uncompress the file. Now, once it does the uncompression, the size will be close to 3.5 GB. Okay, that's the size it's going to take when it does the uncompression. So just keep in mind on the same. All right. Now, once I do this activity, so here I have imported this gensim package. The next thing that I'm going to do is I'm going to make use of a helper function which is known as keyed vector class. And this keyed vector class provides a lot of convenience for me. So best part is it will provide me the function which will help me to load this data into my memory. So I'm going to mention my file path. So model path is equal to, I'll get the complete file path. So I'll refresh it. Once I do the refreshing, yes, so this is the complete file path. I'll say copy path. So here I have noted down where exactly my model is present. Now once I have mentioned my model path, I'm going to load this model. I'll write it like this. I'll say model is equal to gensim dot models dot keyed vectors dot load underscore word to vec underscore format, and inside the parenthesis I'll have to mention my model path, and then this is present in a binary format. I'll say binary is equal to true. Okay, so I'll mention all these things. So once I execute this cell, this is going to load the model from this path. So in order to load the model from this path, I'm making use of this keyed vectors class. So remember, the model size is greater than 3 GB. It will take a while for us in order to load the model. So just have some patience. Now once it's done, we'll be able to see whether it is completed or not. Now, once the model gets loaded, so we'll start by understanding how does the overall vocabulary would look like. Now, what we can do is we can get to know this vocabulary and by displaying its keys. So by displaying the keys of the vocabulary, I can understand what are the unique words that are present over here. So in order to do that activity, see, the model has been loaded. It took a while, it close to 30 seconds, I would say. Now, once that is done, I'm going to say import random. So this is going to import the random module for me. So from random, I'm going to import the choice. So because I'm interested in randomly selecting the data. Now, in order to access the vocabulary, I'm going to say model.vocab.keys. So this will help me to get the list of vocabulary. Now, once I get the list of my vocabulary, if I display vocab colon 5, just display first few entries over here. See, these are the first 5 entries of this vocabulary. Now, if I call the length of my vocab, so this is going to display the overall length. So in the overall length, we can clearly observe there are 3 million words are present in this vocabulary. See, 3 million words are present in this vocabulary, and these are just some random first 5 elements in this vocabulary. And I can display some random elements as well. Maybe I can write a logic like this for I in range 10. Okay, and I'm just going to say print choice. Choice is a function that I've imported from random module. So I'll just get this vocabulary. So this is going to display some random 10 vocabulary items. So Bailey, coach, short track. So these are all the random vocabulary words that I've got over here out of this 3 million words that I've got right here. So let's observe some of the existing words and let's check whether it is part of the vocabulary or not. In order to check whether a particular word is part of the vocabulary or not, I'm going to define a function. I'm going to say check vocabulary, and inside the parenthesis, I'm going to get a vocab, and I'm also going to get the check words, the words that I want to perform the check. So I'm going to define a print statement like this. I'm going to say some 40 character string. Okay, and I'll say mod s, and I'm going to write it like this: word, comma, present. Okay, next I'm going to use the print statement like this, and I'm going to define it in this way. I'll just define some values like this. Okay, now what I'm going to do is, for every word that is present that I want to check in this check words, I'll see if it is present or not. If it is present, yes, I'll say it as present, else I'll say it is not present. Okay, so that's how I would mention. So I'll write it like this: for word in check underscore words. Okay, I'm going to add a print statement here. I'll say print mod 40s. Okay, so here I'm going to say word. Okay, now along with that, I'm going to write it like this. I'll say word in model dot. Okay, I'll check if the word is present in my vocabulary. That's it. So if the word is present, I'll get the output as true, else I'll get the output as false. That's it. So next I'll check if not word dot lower is equal to word. Okay, then I'm going to write it something like this. So what it means is, so here I'm going to check if the word is present or not. If the word is not in lowercase, then I'll have to convert into the lowercase and print the same. I'll just copy this, just a little modification. Next, mod 40s, and I mentioned some spaces like this, and I'm saying it as word comma word dot lower in model dot vocab. So I'll execute this. Okay, now let's assume I want to check the word to vec model. I'll say check vocab. Now here I'm going to send in my vocabulary, and the words that I want to test is Narendra, and let's say Trump, and the other word is data, machine, and let's say another word that I want to test is NLP. So these are the words that I want to check whether it is present in my vocabulary or not. So if I execute this, it says the word Narendra is present. Okay, and here Trump is present. Okay, and data is present, machine is present, NLP is not present. Okay, so that is what we observe on this given data. So I'm going to check whether the word is present or not, and I'm checking whether the full word, that is the camel case, is present, or I'm also checking whether the lower case is present. So we can observe that the word Narendra with capital letter N is actually present in my vocabulary, and the word Trump is also present, data is present, machine is present, NLP is not present. So that's how we can check whether the required word is present in the vocabulary or not. Okay, now I can also check some with some more words as well. So this time I'm going to say Narendra underscore Modi. Okay, then I'll say Donald underscore Trump and United underscore States, United underscore Kingdom. So these are the words that I'm going to check whether it is present in my vocabulary or not. So it says Narendra Modi is not present, Donald Trump is present, United States is not present, United Kingdom is not present. That is what we observe in this given data. Maybe the reason it's not present because, so what I can do is, this time I'm going to make it like this. Okay, Narendra underscore Modi like this, D capital, T capital, so U and S capital, U and K capital. Now let's check whether we have got the multiwords present or not. See, Narendra Modi is present, Donald Trump is present, United States is present, United Kingdom is present. So this is how the words are present in the vocabulary. And likewise, you can test with various topics as well. You can check for machine learning, deep learning, and you can check for some like idioms, or you can also check for misspellings as well to see if there are misspellings or not. So you can do all sort of checks on this vocabulary team. Okay, you can also check the numbers to see whether it is, if it is present or not. So all these things that you can analyze and check whether that particular word is part of my vocabulary or not. Now that you have understood whether the word is present or not, now let's take a look inside a single vector. A single vector will be of the dimension 300. So let's understand how does the range of values would look like. Okay, so in order to do that analysis, I'm going to import the matplotlib library, impress plt, cborn as SNS. Then along with that, I'm also going to import the numpy library. Now, once I do the necessary imports, what I'm going to do is this time I'm going to get a vector representation of a specific word. So I'm going to say vector is equal to model dot word underscore vec, and I'm interested in the vector representation of the word Narendra Modi. I'll copy this and I'll paste it over here. So I'm going to get the vector representation of this word, that is Narendra Modi. Now once I do that activity, I'm going to print the vector dot shape. So if I display the shape, see, the word Narendra Modi is represented with the help of numerical values, and this numerical values is of the shape 300. Let's have a quick check by displaying the vector. See, this contains the numerical real values. Now to get the overall distribution of this data, so let's go ahead and create a displot, that is the histogram chart. But before that, let's go ahead and check some of the properties of these vectors. So since it's a vector, so we can just go ahead and check the magnitude of the vector. I'm going to say magnitude of a vector is, so I'll check the magnitude. I'll say np dot linear algebra dot norm, and inside the parenthesis I'm going to mention my vector. So the magnitude of this vector is 4. That's the magnitude of this vector. And let's have a look into the distribution of the data. So I'm going to say sns.displot. Here I'm going to mention my vector, and I'll mention this KDE plot as false. Okay, and I'm going to mention my rug as true, and then plt.title, and this time I'm going to say histogram of feature vector. Finally plt.show. So once I execute this, we will be able to visualize this in the format of a histogram. See, this is how the histogram would look like. So the overall range, at least if we observe in this data, it's between -1 to +1. So that's the range in which we can see the overall output, the values will be. Okay, so this is the overall values in this vector representation of the word Narendra Modi would look like. So what we have seen is, we have seen how we can load a pre-trained word-to-vec model which has been trained and shared to us by the Google team, how to load the model using the GenSim library, and we have validated that there are actually 3 million words in this vocabulary, and each word is represented with the help of the vector which is having the length as 300. Now apart from that, we also have various functions that are made available to us from the GenSim library. So I can check the similarities between the two words. It is very similar to what we have seen in the demo video, that is in the demo website. So let's go ahead and compare the two words and see how those words are similar together. I'm going to write it like this. I'm going to say score is equal to model dot similarity, and here I can mention the two words that I'm interested. Let's say bread, and the other word that I'm interested is jam. Now once this is done, so here I'm going to print the cosine similarity between them. So here it says cosine similarity between, let's do it in this way. Okay, so word 1 and word 2 is, I'm going to write it like the score. Okay, so instead of mentioning it like this, I'll say word 1 is equal to bread and word 2 is equal to jam. Next, in order to find the similarity, I'll write it like this, word 1 comma word 2. So if I execute this, the cosine similarity between the words jam and the bread is 0.220. Okay. Now this time I'm going to consider bread and butter. So the cosine similarity between bread and butter is actually 0.64, which is closer to +1, which means bread and butter are actually closer together. Now let's try out, and I'm going to say like this. I'll say cycle and bicycle. I hope both of these words are present in my vocabulary. So here the bicycle and the cycle score is 0.16. Now let's go ahead and find the similarities between the words like couch and sofa. So if I find the similarities between couch and sofa, it is closer to +1. That means they are actually very similar. Okay, so in this way we can find the similarities between one word to the another word with the help of cosine similarity. So if the words are similar together, we will have the maximum value as 1. If the words are dissimilar, then in that scenario we'll have the minimum value as -1. So this is how we can find the similarity between the words. Okay, and apart from finding the similarity, we can also get the most similar words to the words that I'm interested in. So most similar words. So if I want to get the most similar words for the words that I'm interested in, so I can write it like this. Suppose if I have the word as sofa. So for the word sofa, if I want to get the 10 most similar words, I can write it like this. Results is equal to model dot most underscore similar, and inside the parenthesis I'm going to mention the positive is equal to word. Okay, so I'm going to mention the top n. Okay, top n is equal to 10. So what this is going to do is, when I say positive, positive words contribute positively towards the similarity, and negative words negatively. Okay, so positive means list of words that contribute positively. Negative means list of words that contribute negatively. Top n refers to the number of words that it has to return. So I'm returning the top 10 most similar words to the word of sofa. Now here I'm going to print results. So the top 10 words which are similar to the sofa will be given to us. So this will take a while because the model has to check the each and every vector representation, and then it has to load the similar items for us. Okay, so if you're using the free version of Google Colab, so at that time you might get the system timeout error. So in order to avoid it, you can go ahead and run it in your local system, or you can purchase the Colab version, which is purely optional, which is not relevant for us. But just to give you an idea, when I run this code, this will give me the similarity, that is the words which are similar to the word sofa. Okay, that's the code, that's the output that we would get. Okay, now before I end this video, I want to show you as how to calculate, okay, how to calculate the similarity score between two words. Okay, that's what I'll be showing you right now. So when I talk about the finding the similarity score between the pair of words, so we make use of cosine similarity. The cosine similarity is given by, suppose if I've got two vectors x and y, then cosine similarity between x comma y is equal to vector x dotted with vector y divided by magnitude of x multiplied with magnitude of y. So this is the formula for the cosine similarity. Now let's go ahead and let's pick up some words. Okay, let's pick some example words. Let's say I'm going to consider the words of bread and butter. I'll consider these two words, and once I consider these two words, I'll manually find the cosine similarity between those two vector representation and check whether I'm getting the same value like this here or not. So first thing is I would require the vector representation of these words. In order to get the vector representation of these words, so what I'll do is I'm going to get the complete Gensim matrix. So in order to get the complete Gensim matrix, I'm going to write it like this. I'll say matrix is equal to model dot vectors. And once I do that, I'm going to write it like this. I'll say shape of matrix is matrix dot shape. So this matrix is of the shape 3,000,000, 300. So this matrix contains the complete word embedding matrix. What I have to do is from this 300 million rows, I have to get a specific row which represents the words which is of my interest. So in order to do the same, I'm going to write it like this. W1 is equal to model dot vocab, and the word that I want to extract is bread, and here I'm going to extract its index position. And for the second word, I'm going to consider the word that is bread and the other one is butter, and I'll get its index. Now once I extract the index, what I can do is if I want to get the vector representation of my individual words, I can say v1 matrix, and I'll get that specific row, that is w1, and I'll extract all the columns. Similarly, I'm going to extract the vector representation of the word 2. So w2 colon blank. Now once I have these values, if you look into this formula, I would require the magnitude of x and the magnitude of y. So magnitude is nothing but the norm which I have shown you earlier. So let's go ahead and print the same. I'm going to say norm of w1. So what is w1? So I'll just write it like this. Norm of bread is, okay, and here I'm going to compute as np dot linear algebra dot norm of v1. So this will describe the norm of v1, and I'll say butter, and here I'll mention my v2. So I'll get the norm values for the individual words, that is bread and butter. Now let's go ahead and find the values right here. So what I'm going to do is I'm going to write it like this. I'm going to say v1 norm. Okay, so see the overall formula is, okay, the overall formula is x dot y divided by magnitude of x into magnitude of y. So let's go ahead and perform this activity. First, let me take the dot product between v1 and v2. So that's the first activity that I'm going to do right now. So cosine similarity is equal to np dot dot, okay, I'll say v1 comma v2. So this will be the dot product, the numerator, and this is divided by, the entire thing is divided by the denominator term. So in my denominator term, multiply the values. Okay, I'll just substitute over here in the formula. Next, I'm going to print cosine similarity is, and I'm going to print this cosine similarity value. So once I execute this cell, see the cosine similarity that I've got is 0.6417, which is similar to what we have got from the Gensim package. Alright team, so what we have done as part of this hands-on exploration of this model is, so we have loaded this pre-trained word embedding model, which is a word-to-vec model, and we have seen how the similarity score is actually calculated. We have implemented from scratch, and we have also made use of Gensim package as well. Now for finding the most similar words, this will take a lot of RAM. So even if I execute it again, I'm going to get an error because it's going to consume a lot of space in the memory. And as a result of this, I might get the timeout error or the compute error since I'm using the free version of Google Colab. So it's an optional step. If it works, you can check, else you can ignore it. So we'll be working in depth in the next session where we will understand how these models are actually trained. So with this, we come to the end of this video. In the next video, let's go ahead and learn about the modeling technique that is in the word embeddings. In this video, we are going to learn about the skip-gram model architecture in the word embedding. As we have studied in the first video, under the word embeddings, we've got two variants. One is skip-gram architecture and the continuous bag of words. So as we proceed in this video, we are going to understand what exactly is the skip-gram model architecture. Now, if I want to show you and talk about this skip-gram architecture at a very high level, so this skip-gram architecture is actually a very simple neural network. So here we will make use of the data set and tweak it in a certain way so that we are going to perform the required task. Now, this is a diagram which talks about the comparison between the continuous bag of words and the skip-gram approach in the scenario of the skip-gram approach. So here, the skip-gram is used to predict the context of the word for a given target word. So that is the overall idea. I'm interested in predicting the context word for the given target word. Now, let's get a clear understanding as how it actually works. In order to explain the same, now here when I talk about this word-to-vec model, so this word-to-vec model uses a trick which you have already seen in the machine learning domain. So what we do is we are going to train a simple neural network. We'll train a simple neural network, and this neural network has one unique feature. That unique feature is it has got only one hidden layer. So with this single hidden layer, I'm going to perform a simple task. But the thing is, whatever the task that I'll be training, I'll not use my neural network to do the task. Instead, what I will be interested is, I will be interested in the learned parameters. I will be interested in learned parameters. So what are all the learned parameters in my neural network? Which are nothing but the weights. The weights that I have learned in my hidden layer, that is what I will be most interested in rather than the task that I have actually performed using my neural network. I know it's very unique, but that's the beauty of this word-to-vec model, and you're going to understand more and you're going to enjoy more as you learn about this technique of this word-to-vec model. So what happens whenever we are training this neural network is we are going to perform a dummy task. So we are going to train our neural network such that given a specific word, okay, given a specific word in the middle of the sentence, we are going to look into the nearby words and we are going to pick one at a random. So given the middle of the sentence, I want to pick up the nearby words. Okay, so here this neural network that I'll be training, that neural network is going to tell me what is the probability of every word in my vocabulary being the word which is near to the word that I'm interested in. Now when I say nearby, it is nothing but we generally refer it as a window size. We'll come to the window size very shortly as we progress, but observe, just remember that given a middle of the sentence, I'm interested in looking into the nearby words. So the overall output that I'll get from my neural network, this is going to tell me in terms of probability. So it will tell me as how likely I'm going to find the next word or the related words given a specific word. For example, if I have a word like New Delhi, okay, if I have a word like New Delhi, so given this word, the New Delhi for my model that is on my neural network, the output probabilities will be much higher for the words like India, Bharat, compared to the words like China. Okay, so that is the overall idea. So the words which are very similar to the word that I have given for my neural network as an input. So the words which are similar to it will have the highest probability scores compared to the words which are unrelated to the words that I'm actually working with. Now, what we do is we are going to train the neural network in order to do this activity automatically. And while doing it, I'm going to feed it with the help of word pair, which is actually found in my training documents. Now, to help you understand this concept, Let's go to the link that we have seen earlier to look into the demonstration of this word embedding. So this is the link that we have seen in the first video about the word embedding. So here, as an example purpose, I'm going to place a text. Okay, here I've placed the text or a sentence as a quick brown fox jumped over a lazy dog. Okay, this is the text that I have mentioned right here. Now, since we are discussing about the skipgram, I'll select the model as skipgram, and for the example purpose, I'll specify the window size as 2. Okay, so once I do that, I'm going to generate the data set. So now, if you look into this scenario, okay, on the left hand side, I have got the token, and on the right hand side, this has generated the training example. So the training examples are the pair of examples. The pair of examples are A quick, A brown, quick A, quick brown, quick fox, brown A, brown quick, brown fox, and brown jumped, fox quick, fox brown, fox jumped. So this is how we have generated the training examples for this given data. Now you might be wondering, how did the system come up with such training samples or the training examples? So the way this training examples will be generated is with the help of the window size. Suppose if I mention the window size as 2, what it is going to do is, for each word, it's going to look into the window size as 2, and with that window size as 2, it is going to generate the samples as the input and output. For example, in this scenario, I've got a quick brown. So here I'm going to consider this entire text over here as an example. And with the pool window, that is in the scenario, the window size as 2, it is generating the data. I'll take the screenshot and we'll have a deeper dive into the same. Now, suppose let's start with the first word, that is A. So here with the first word as A as an input, okay, it is going to generate the combination of its output with the window size as 2. That means it will take 2 steps towards right and 2 steps towards left. There are no words on the left hand side of the A, so I'm going to consider 2 words as the pair of outputs. So it says A and quick is one pair and A and brown is another pair, which is what we had seen earlier. Okay, now once I have completed the window size as 2, I'll move to the next word. The next word is actually quick. So it takes 2 steps to the right and 2 steps to the left. So 2 steps to the right means quick and brown and quick and fox. 2 steps to the left, there is no 2 steps, there's only 1 step. So quick A. So quick A, quick brown, quick fox. Quick A, quick brown, and quick fox. So this is how I've generated the training example. Next, it moves to the next word. Let's say it starts with brown. Now this time when I'm interested in the word brown, when I'm generating the data, so I'll take 2 steps towards right and 2 steps towards left. So the pair of training examples that I have are brown and fox, brown and jumped, brown and quick, brown and A. So let's come down over here and let's validate. See, brown A, brown quick, brown fox, brown jumped. So in this way, we are going to generate the training data. So what I have done is, with my given text corpus, I have generated the pair of training samples. So here, while generating the training samples, I'm going to specify the window size, and window size is something which is going to decide, okay, which is going to decide how does the overall data would look like. Okay, how does the overall data would look like? Now in this scenario, I'm interested in predicting the nearby words given the center word, which means if I am given with the A as a center word, I'm going to predict the nearby words to the A. Hence my training example says A and quick, A and brown. Now, if I'm given with the word quick, I'm interested in predicting the nearby words, that is brown, fox, and A. In the same way, if I'm given with the word brown, I'm interested in finding the nearby words with the window size too. So fox jumped, quick, and a. So this is the overall idea behind this skipgram approach. Okay, so we are going to generate the training samples. We'll generate the training samples such that, connecting back to our slide, I'm interested in predicting the context word for the given target word. That's the core principle behind the skipgram. Given the particular word, I'm interested in finding its nearby words. Now that this concept is clear, so you are sure as how does this data is actually found. So we'll take a pause over here. Let's continue in a learning journey and understand about the model architecture in the next video. So I'll see you in the next video. Okay, let's continue in a learning journey and let's have a look into the model architecture of this approach, that is the skipgram approach. See, when we talk about this model architecture, first thing is the input. In the previous video, we have looked into our input. So we have seen how does our input would look like and how does our output would look like. So in this scenario, the input is a string value and the output is also a string value. But you know already, if I have a neural network, I cannot use the string value as it is. So what should I do? Yes. So the first thing that we are going to do is we are going to build a vocabulary of the words. So once I build the vocabulary of the words, now let's assume in my vocabulary, I'm going to have 10,000 unique words. There are 10,000 unique words in my vocabulary. If I have 10,000 unique words in my vocabulary, then I can represent an individual word with the help of one hot vector, and each vector will have 10,000 components, and this is what you're familiar with already in the previous section. So let's suppose if I have a word John. So if this word John is part of 10,000 unique words, then this one hot representation of the word John is given by 0, 0, 0. Somewhere in the position of John I'll have as 1, and rest everything it will be 0. And the overall length of this vector will be 10,000. So this is called as a one hot vector. I'll place 1 in the position corresponding to the word John, and in all the other position I'll just mention it as 0. So this will be my input. My input will be the one hot encoding representation. Now what will be the output? Now in the scenario of output, okay, so output will also be a one hot representation. The output of the network will also be a one hot representation. That means it is actually a single vector. So this has the length as 10,000. So I would expect a single word in the output. Now, obviously, in the scenario of prediction, I cannot have a single value as a one hot encoding. So we are going to fine tune a bit and we are going to say that, okay, in the output layer, I will be giving the output in the format of probability. Maybe we'll apply the activation like a softmax, which will give me the overall highest probability scores for the word, which is I'm expecting for the output. So that is the overall architecture of my neural network. So if I now want to describe this architecture, so my input will be something like this. Okay, this will be my input vector. This input vector will be of the size 10,000, assuming that I have got overall 10,000 unique words in my vocabulary. And as I mentioned earlier, this will be connected to a single hidden layer. There's only one hidden layer. And we are going to have an output layer. So this is my output layer. In my output layer, I'll also have the 10,000 will be the shape of my output layer. But this time in my output layer, I'll have a softmax activation function. So input vector is an one hot encoding. Okay, this will be my one hot encoding, and the size of my one hot encoding is dependent on the size of the vocabulary. So this is how we are going to create our neural network. Now in the middle, I have mentioned a hidden layer. Now in the hidden layer, there's no activation that we have over here. Okay, but only in the output, I'm going to use the softmax activation function. So that's one key thing that you have to remember. Now, whenever I'm training this neural network, I'll be training this neural network with the help of word pair. Now, if I want to give you an example, which is what we have seen earlier, let's say if I've got the input as A and the output as quick. So I'll have the input as A and I would expect the output as quick. So this A, it will be represented in the one hot encoding like this, 0 0 0 0 1 somewhere 0 0, and my quick is somewhere like this. For the position of quick, I'll have the highest probability, maybe 0.9. Rest everything I'll have very small value, 0 0 0, something like this. This is how the input and output of this neural network would look like. Okay, so the label will be a quick, which is actually my one hot encoding representation, but the prediction, it will be in the format of a probability distribution. So this is about the input layer and the output layer of this representation, that is our model, that is the word embedding. Okay, with this understanding, I'm going to draw a box. Okay, I'm going to have an input layer like this. This will be my input layer. And then I'm going to draw one more box. This is for my hidden layer. And I'll draw one more box for my output layer. Okay, this is how the overall architecture would look like. This is my input. Assuming that I have got 10,000 unique words, this will be the shape. And even this is my output. Assuming that I've got 10,000 words, obviously the length of the vocabulary, that will be the shape over here. And in this output layer, I'll have a softmax activation function. So this is what we have learned till now on this word embedding. Now let's focus on this hidden layer. Now let's consider as an example, we are going to learn the word vectors which is going to have 300 features. So I have decided that each vector that I'll have, that is the each word that I'll have, I will be representing my individual word with the help of 300 features. So in my hidden layer, we are going to represent it with the help of a weight matrix where I will have 10,000 rows, where one row for each word that I've got over here in my input corpus, and I'm going to have 300 columns where one column for each feature, that is one for every hidden neuron. So in other words, in my hidden layers, I'm going to have 300 neuron, and there will be a dense connection. I'll just write it like this, and I'll write it as there will be a dense connection. So what is dense connection? Every neuron in my hidden layer. Suppose this is a one neuron in my hidden layer. Every neuron is connected by every other neuron in the previous layer. In other words, every other inputs, that is 10,000 inputs, will be going to each and every neuron. And if I represent it, so that is how I'll be representing it in the format of a matrix. So I'll have the number of rows as 10,000. Okay, and 300 as the columns. So this is how I'll be representing my hidden layer. So 300 is the features, and the reason that I'm writing as 300 because that's the same number of features which Google has actually used in their research paper. So hence I have used the same as of now. So the number of features, that is the length of my overall word embedding, is a hyperparameter. You can also fine tune it as per your requirement. For the example purpose, I'm going to consider the value as 300, and there are 10,000 unique words in my vocabulary. Now, if you look into the rows that have got over here, so the rows of my weight matrix are actually what will be my word vectors. So the reason that I'm going to call it as a word vectors, because imagine this. I've got the number of rows as 10,000. So for each word, I'm going to have an individual row over here. The reason that I'm saying it as an individual word, because let's take up an example. Let's say I have got 10,000 words in my vocabulary. Now, if I represent an individual word, to ensure that we are going to perform the mathematical operation in an effective way, I'm going to represent this 10,000 word vector with the help of the dimension 1, 10,000. So single row with 10,000 columns. The reason is, so each word is represented in the format of one hot. Let's say my individual word, the input word, is actually called as brown. Okay, now let's say I'll have the word one hot encoding like this. Okay, for the demonstration purpose, I'll just mention it like this, where I'll have 1 over here and rest everything will be 0. And each and every row over here, it expects, it is actually the weight values. Now if I take the matrix multiplication between 1 comma 10,000 with 10,000 comma 300, so this would result in the shape of 1 comma 300. Now what is 1 comma 300? It is nothing but selecting a specific row where I have the value as 1. So that is the overall idea about getting the weight values. So to help you visualize this in an effective way, let's say I've got the one hot encoding representation like this 0 1 0 0, and I've got the weight vector of the shape like this. So this is of the shape 1 comma 4, and I've got the weight vector values like this, let's say 50 60 70 12 6 7 13 10 8 9 12 13. So suppose this is of the shape 4 by 3. Now if I take the matrix multiplication between the vector and this matrix, so this will result in the shape of 1 comma 3. And which 1 comma 3? So only this row where I have as 1, only that row will be selected as an output. So 12 6 7. So what it means is this is going to effectively select the matrix row which is corresponding to the value 1. Now coming back over here in my model architecture, I have the input which is of the shape 10,000 because each dimension referring to my individual unique word in my vocabulary, and I'll have everywhere as 0 except the value 1 for that specific word. Now when I multiplied with this hidden layer, that is with my hidden matrix which is having the shape as 10,000 comma 300, it is going to effectively select the matrix row which is corresponding to the value 1. Now here in this very small example that I just took you right now, it has actually selected this specific row which has the value equal to 1. So the hidden layer of this model is really just operating as a lookup table for us. The output of my hidden layer is just the word vector for the input word. So whatever I've got the input word, so for that word, this is the word vector representation. So team, are you with me till here? So just think about it. I've got everywhere mentioned as 0. In only one place I have as 1. And this will be my weight matrix. Now, once I have this weight matrix, it is just selecting that specific row wherever I have as 1. Now, what is the output that I'm getting as a result? As a result, I'm getting the output as 1 by 300. Okay, 1 by 300 is the vector that I'm getting right now. If I'm processing the word for brown, so 1 by 300 is a vector, which is the vector representation for the word brown. So in this scenario, I'm saying it as a vector, but if you think from the perspective of the neural network, these are all just the parameters that I have in my neural network. Now connecting back to my neural network, see, this is my input, and for each and every input is being passed to my hidden layer. So each and every input is being passed to my hidden layer. Let's say I have got 300 neurons over here. So if I do the matrix multiplication, it's nothing but taking the matrix multiplication between my vector and the weight matrix. So that is the overall idea about the working of this hidden layer. So when the overall idea is whatever the input that I'll have, I'll get its vector representation with the help of my hidden matrix. The output that I get as a result of multiplication, that's the word representation of the input word. That is the embedding representation of the input word. Now what I'm going to do, so whatever the output that I get, see, once I do this multiplication, I'll get the output as 1 by 300. That's the output that I'll get as a result of performing this matrix multiplication. So this 1 by 300 data is then fed into my output layer. Now in my output layer, I've got the softmax activation function over here. Okay, so what it does is each output in my data is going to get an individual neuron, that is one per word in my vocabulary, and it is going to produce an output between 0 to 1. Okay, so it specifically means that each neuron over here, okay, so each neuron over here has a weight vector which is then multiplied against my word vector that I've got over here. Okay, now once I do the multiplication, I'm going to apply the e power to the result, and finally in order to get the output to sum up to 1, I'm going to divide the result by the sum of the result from all 10,000 output nodes. So that's the overall idea behind the softmax activation function. You can check out the mathematical formula if I want to explain it in the visual manner. So the way it is going to work is I'll have a 1 by 300. So this is of the shape 1 by 300, which is the outcome of multiplying my input with the hidden representation. Okay, next, so what I'm going to do is I'm going to have an softmax activation function. So I'll have the softmax activation function. So the softmax activation function is given by e power x divided by sigma e power x. We'll apply the softmax activation function. So once I have the softmax activation function, this is going to result in the output of probability. Okay, so this is how the data would flow through from my input layer to my output layer. Now that you have understood how the data would flow from my input layer to my output layer, I'll come to this part. So I've got the input layer, this is my hidden layer, and this is my output layer. So now that you are aware as how the data would flow through from left to right, now let's build some intuition behind the same. Now let's say if I have two different words, and if I have two different words which has got a similar context, which means here when I say context, each words has these similar words which are appearing around them or the similar words nearby to them. Then in such scenarios, our model needs to output the same result for those two words. And one way for the neural network to output the similar context prediction for these two words is if the word vectors are actually similar to each other. So it means that if I've got two words and if two words have similar context, that means if I have got two words and if these two words are having the same nearby words, then in such scenarios, our model that we have got, that is our network that we have got, this network is motivated to learn the similar word vectors for these two words. So this is an exciting part. So let me just give you an example. Now, what is the core idea of the generation of the data set? See, the core idea for generation of this data set is I'm going to get a pair values, that is a training pair value. Considering the value that I have got over here in the middle, I'm interested in predicting its nearby words. So with this context, I have prepared my training data. So if I have a training data like this, let me bring back the scenario, that is the screen. See, I've got the data a quick, a brown, quick a, and something like this. So the idea is, okay, if the word quick has the word brown, okay, and let's assume if I've got another word, let's say fox, and if this fox is also nearby to the word brown, then it is an overall understanding that both quick and fox will have the similar word representation, because for both quick and fox has the same nearby word, that is brown. So that is the core principle behind this word to vector representation. Let me write it over here so that you can process this very important information. If two words have similar context, Then the neural network learns word vectors for those two words. So this is the core principle behind this skipgram. So here, when I say two words have the similar context, so you can expect those words to be synonyms like intelligent and smart, or it can be the similar sounding words like or similarly used words like engine and gearbox, engine and accelerator. So those are all the similar context. Okay, and these similar contexts can be the words with its plural form as well, like bike and bikes. So all those things, okay, all those things will have a similar representation of the word vectors. So what we have started is we started with the dummy task. So what is the dummy task? The dummy task is getting the training data. Okay, once I get my training data, we are going to specify the window size, and using this window size, we are going to generate the training data set, and we are going to train a neural network between this input and output. Now, while training while training with the training examples of input and output, we have actually understood the hidden representation, which is nothing but the word vector representation. Now, this ultimate, the word representation that we have got after I have trained through like a humongous volumes of data. So that is the word to vec matrix that we have got. Which means once I have trained the model between this input and output, I'm going to throw away the output. I'm going to throw away the input. I'll just keep only the hidden representation. The hidden representation is nothing but the hidden layer matrix, which is having the shape as number of vocabulary items by number of dimensions for the features. Okay, so that is the dummy task that we have performed in order to generate this word embedding matrix. So this dummy task that we have performed, so this works really best because here in order to train this, okay, in order to train these kind of dummy tasks, I don't have to worry about preparing a very long list of sequential data and the label data. I can just make use of large text corpus that is present with me. I can apply some pre-processing technique and prepare the text data. So that's how easy it is to build and train these skipgram models. So now that you have understood this skipgram technique, so what we will do is we are going to reinforce our understanding by implementing it in the format of a code by writing the code from scratch. So we'll write the code from scratch so that you will get a clear idea as how it is actually working. So we'll deepen our understanding with the hands-on approach in the next video. I'll see you next time. In this video, we are going to train the skipgram model. So as we progress in this video, we'll take up the hands-on approach in training a skipgram model, which we have learned in the last few videos. And then we are going to explore about the forward pass. So in the last video, I have explained as how the forward pass is going to happen in the scenario of skipgram. So once we train the model, we'll take up the example data and we are going to apply the forward pass and see and validate the result. Okay, so let's get started. In order to do this, I'll start by launching my Google Colab. And here, first thing that we would require is we would require the data set. Along with the data set, we have to install the gensim library. I'll say pip install gensim. And along with that, there's a module called Python Levenstein. I'm going to install the same. So Python. Okay, now once I do the installation, I'll begin by downloading the data set. So the data set that I'm going to download, it's from the Stanford University. Okay, so this data set is about the reviews of cell phones and the accessories. So that's the data set that I'm going to download right now. So this is going to download the data directly from the Stanford Education website. And from there, we will get started. Currently, it's in the format of GZ format. Now we will have to do the unzipping. So gunzip, and I'll specify the file name. So this is the file name. Okay, so this will take care of unzipping the same. So currently unzipping is in progress. So yes, the unzipping has been completed. So once the data has been unzipped, so let's go ahead and import the necessary libraries. I'm going to import the GenSim library, and along with that, I'm going to import the Pandas library. Now, once we do the necessary imports, here in this scenario, the data set that we are working is the Stanford University's data set, which is the Amazon reviews from a cell phone and the accessories category. Now, this data that we have got, this is stored in a JSON file format. So since the data is actually stored in a JSON file format, we can actually make use of Pandas library and read this JSON format. So to load it as a data frame, I'll make use of the function pd.read_json. Here inside the parenthesis, I'm just going to get the path and I'll mention the complete path. And I'm going to say lines is equal to true. So in this way, I'm going to read this JSON file. And if I display first few entries of this JSON file, that is this data frame right now. So this is how the overall data would look like. We've got the reviewer ID, ASIN, reviewer name, whether it was helpful or not, and review text, what is the review text it conveyed, and then overall rating, what is the summary, and the review time, and the overall scenarios that we have got right here. Okay, so this is the overall data that we have got once I download the data directly from the Stanford website. Now, if I describe the shape of this data frame, so this data frame is of the shape 194,439 rows and 9 columns. Now, once we have the text data, the first thing that we are going to perform is we are going to perform the pre-processing and the tokenization. So pre-processing helps me to clean the data, and then tokenization will help me to split my entire document into individual parts so that my model can go ahead and generate its word embedding. So in order to do this activity, so I'll just go ahead and make use of the simple pre-process which is present inside this GenSim library. Now this simple pre-process, let me just show you how it actually look like. Okay, so here, and this is actually present inside this GenSim utils simple pre-process. If we go to the official documentation of this simple pre-process, so this is going to convert my document into list of lowercase token, and here it is going to ignore the token that are too short or too long. Okay, now internally it is going to perform the tokenization by making use of the method tokenize internally. So this is how I can access this simple process. So this is present inside the gensim.utils.simple_process. So the parameters it expects is the document, that is my input string, and it also expects the minimum length and maximum length. We can just specify it as per our requirement. Okay, so in order to do this activity, so let's take up an example text data. So here in this data frame, the review text is a column which contains the text data. So df review text, and here if I just get an example text, this is how the example text would look like. Now I'll just copy this text. Now I'll write it like this: gensim.utils.simple_preprocess, and inside the parenthesis I'm going to mention this text. Now if I execute this, see, as a result, this has converted the text into lowercase and it has automatically performed the tokenization. Now for the demonstration purpose, I'm making use of this simple pre-process. If required, you can also make use of your own favorite pre-processing libraries. It could be NLTK or it could be Spacey. The expectation is I want to perform the activity of this tokenization on the given data. Now if I want to apply this function on each and every row on this given data frame, so I can just write it like this. I'll say review text is equal to df review text. Okay, and on this column I'm going to apply the function. So the function that I'll be applying is gensim dot utils dot simple underscore preprocess. Once this is done, if I now display first few entries of this review text, so this will take a while because we've got more than 194,000 rows in our given data set. And this simple preprocess has to apply on each and every row that I've got on the text data. And once that is done, if we display the first few entries, we should be able to confirm that the given data, that is the string data, on top of that, we have performed the tokenization by converting it into a lowercase. Okay, so in this way, we can validate the same. Now, once we have got the data, next what I'm going to do is we'll go ahead and train this word-to-vec model. So that's the first activity that we are going to do. We'll train our word-to-vec model from scratch using this text data, and then we are going to understand more about the forward pass. So let's train the word-to-vec model. Now, while performing the training, you have already learned that we have to prepare the data for word-to-vec model. For preparing the text data, so we have to specify the window size. So window size is one important parameter which describes as how my training data will be actually created. And along with that, we can specify any other condition. So we can say that minimum count as 2. That means if I have any vocabulary, if it is used at least twice, then only I'll consider it as a valid word. So we can mention all those conditions whenever we are initializing this word-to-vec model. So in order to initialize the model, I'm going to write it like this: model is equal to gensim dot models dot word-to-vec. And inside the parenthesis, we will have to mention the window size. I'll write my window size as 10. So this is the size of my sliding window. Then I can mention the size. So size is nothing but what should be the size of my feature vector. In this example, I'm mentioning it as 100. So my feature vector will be of the shape 100. And we can mention the minimum count. So minimum count, I'll mention it as 2, which means that here this word should be considered at least twice. Okay, a sentence with at least 2 words should be considered. So if I've got a very less sentence, less than 2 words, I'll not consider it as a valid sentence during the pre-processing. Now, in order to apply the learning that we have learned in the previous session, so if I want to implement this skip gram, I'll say SG is equal to 1, which means I'm going to apply this model of skip gram for a given data. So this is going to initialize my model. Now, once I have initialized the model, the next activity that we have to perform is we have to build the vocabulary. Now, in order to build the vocabulary, I'm going to say model dot build underscore vocab. And inside the parenthesis, I'm going to mention my review text. So this is going to learn from the review text that I have got. So my vocabulary will get built from this given text data. Now, along with that, we can also specify the required values. So by default, epochs is set as 5, and we can also modify the epochs if you would require. For example, if I say model.epochs, so by default, the epochs is set as 5. So if I want, I can increase the number of epochs as well as per my requirement whenever we are whenever we are doing the training. And we have got the model.window. So this describes the length of my sliding window. So here it is mentioned as 10. Now, once we have built the vocabulary, let's go ahead and train the word-to-vec model. In order to train this word-to-vec model, so first thing that I have to do is I'll just have to call model.train. Here I'll have to mention my review text, and we will mention the total examples is equal to model.corpus underscore count. Okay, and for epochs, I'm going to mention as model.epochs. So this is going to train the word-to-vec model. Now, once the word-to-vec model has been trained, we can then go ahead and save the model. So this will take some time in order to complete the training, since in this example we are going to train from scratch, and most importantly I'm just training it for only few number of epochs. You can go ahead and increase the number of epochs, but for the benefit of time and the benefit of learning, I'm just training for only 5 epochs. So number of epochs, just like any deep learning model, we can increase the number of epochs so that my model have more opportunity to learn from the data set. Now, here I have mentioned my total examples as model.corpus count. So if I go ahead and access this model.corpus count, so this is going to tell me the total corpus count that I have got. Now, once the model has been trained, okay, we can go ahead and save the model. In order to save the model, it's very simple. We can simply say model.save and mention the complete path. Let's assume I want to store it in the current directory itself, and I'm going to say final word2vec dot model. So this is how my model will be saved. Now, once I have saved the model, I can then go ahead and find the similar words. Okay, find the similar words and similarity between the words. Here, in order to find the similar words as well as the similarity between the words, one thing which is very important for us, that is the word embeddings. So once I train my model, that is word2vec model, using this text corpus, this is going to generate a data, and majorly this is going to generate my word embeddings for each and every text that I've got over here. That is each and every tokens that I've got over here. For each and every token in my vocabulary, it's going to build the word2vec representation. And this word2vec representation will have the length as 100. And once I have got this word2vec representation, the matrix has been built, then I can access the individual words vector representation, and on top of that I can apply the various functions, like I can find the similarity between the words, and I can also find the similar words to the words that I have got. Okay, so that's the activity that we can perform. So I'll wait for a while until the model training is complete, and then we are going to proceed ahead in this execution part. Okay, so the execution is now completed. We have trained the model, and after training the model, we have saved the model. So I have the saved model present right here. Okay, now once the model has been saved, we can use this word embedding to find the similar words as well as similarity between the words using those word embeddings. Let's suppose if I want to find the most similar words for the specific word. So model.wv dot most underscore similar. So this is a method that we would use to find the similar words that I've got, and I'll mention it as bad. So if I mention as bad, okay, and if I simply execute it, this is going to return me the top words which are similar to the words that is bad. So terrible, horrible, poor, uncanny, good, and we also have the values. So these values are the cosine similarity scores. So how much similar this word bad's vector representation with the terrible representation. Okay, so that's the score it is going to specify for us. Now, if I want, I can also go ahead and compute the similarity as well. Now, this similarity and all these similar things that I'm finding over here, this is from the model that I have actually trained. So I'm going to say model.wv.similarity. Now, inside the parenthesis, my word 1, I'll mention it as cheap, and for word 2, I'll mention it as inexpensive. Now, if I execute this, this will describe the similarity between these two words. So here it says the similarity between the word cheap and inexpensive as a result of learning from this data set is 0.6379. That's a similarity score that I've got right here. Okay, so in this way, I can go ahead and find the similarity between the words. Now, as I mentioned, once I train the model, what we will have is we are going to have the word embedding vector. Now, let's get the word embedding vector matrix for the entire text values that I've got, that is my entire vocabulary that I've got. So if I say matrix, and I'm going to extract the word embedding matrix from the model that I have trained. In order to extract the word embedding matrix, so it is model.wv.vectors. So this is going to extract the word embedding matrix. Now here, if I describe the shape of the matrix, word embedding matrix is, so if I say matrix dot shape, so the shape of my word embedding matrix is 35561, 100. That means in my text corpus, it has actually found 35561 words. So these are the unique words that are part of my vocabulary. And for each of the words in my vocabulary, I have represented it with the help of a word embedding vector, which has the dimension as 100. So this is my word embedding matrix. Now let me help you by getting a high level intuition by creating a visualization. So whatever the word embedding that I've got, so this is my word embedding matrix. Okay, now this has the shape as 35561 and 100. So 35561 is the number of words in vocabulary. Okay, 100 is the dimension of word embedding. Now, whenever I'm training any model, especially in this word-to-vec model, so I'm going to send in the input. So what is the input that I'll be sending? I'll be sending the input in the format of a one-hot encoding. So what will be the dimension of my one-hot vector? My dimension of one-hot vector will be the dimension of number of words that I've got in this vocabulary. So it will be of the shape 1, 35561. So suppose if I have a single word, one hot encoding that I've got. So I've got 35560 values to be equal to 0. Somewhere I'll have as 1 and rest everything will be 0. And this is my matrix which has a dimension as 35561. So what I'm going to do is I'm going to get the embedding representation of the word that I've got. Suppose if I have the word as brown. So for this word brown, this is the one hot encoding representation. When I do the matrix multiplication, I'm going to extract that specific row, which corresponds to the embedding representation of the word brown. Okay, so that is how we are going to query the given data. I'll take the matrix multiplication and I can get that weight values. Now, once I have this weight values, so this is going to result in a dimension of, let's say, 1 by 100. I'm just giving you an example. This is going to result in a dimension of 1 by 100. Now, in an output layer, okay, we are going to have a softmax, isn't it? So in an output layer, I'm going to have a softmax. So in my output layer, if it is a softmax, even it will have the 35561 dimension, and this will be the softmax. Now, in order to ensure that, we are going to get this dimension as 35561. So what I'm going to do is there will be a matrix multiplication which will happen. Okay, so this will be multiplying with the output, like output matrix. So we are going to have 1 by 100 multiplied with, I'll have an embedding, I'll have a output matrix, we'll have some kind of an output weights. Okay, we'll have the output matrix and this will be having the shape as 100, 355. So once I do the matrix multiplication, this would result in the shape as 1, 35561. Okay, so what I'll be doing right now is we'll take up the one hot representation, we'll get the word embedding representation, and we are going to multiply it with this weight value and apply the softmax activation so that we can get the outcome as how it actually look like. That's the simple activity, yet the deeper understanding that we are going to have on this forward pass. So currently I have this word embedding representation. Now if I want this output vector representation, I'll call this as W out. So if I want to get this W out, so I can get it from the train model. So I can simply write it like this. I'll say W out is equal to model dot trainables dot sin1 neg. Now if I describe the shape of this W out, so this will have the shape as 35561, 100. So that's the dimension of my W out. So here I'm expecting the dimension of 100, 35561, but I have the dimension as 35561, 100. So if I have to do this forward pass, I have to take the transpose of this W out, which we will take it as we progress with the implementation. Okay, this is my output weights. Okay, this is my output weights. We have got the word embedding matrix and we have got the output weights. Now what I'm going to do is I'm going to get my vocabulary list. So my vocab list, I can get it by calling the model dot wv dot vocab. Okay, this is going to get me a complete word embeddings vocabulary list. So if I execute this and display the length, okay, so length of my vocabulary list is 35561. So if I display first few entries of my vocabulary list, so this is how the first few entries of my vocabulary list. Okay, let me just show you some examples. Vocab list. This is how the vocab list would look like. Okay, so this is what my vocab list is containing. It contains the entire vocabulary that I have got over here. Now what I'll do is, for the easier management, I'm going to convert it into a Python list. Next, I'm going to mention it like this. I'm going to get as my vocab length is equal to len of my vocab list. Okay, I'm going to store it in a variable which I'll be using it at a later point. Then the complete vocabulary and its weights, I'm going to extract it and store it in another variable called vocab. I'll say vocab is equal to model dot wev dot vocab. So if I execute this, this is going to return in a Python dictionary called vocabulary. So this contains the value, that is the key is nothing but the vocabulary word and its keyed vector, that is the vector representation of my individual term. Okay, this is what this variable vocab is now containing. Now if I want to get a specific value, okay, if I want to get a specific value, let's say I want to find the index of this position sum. Okay, in that scenario I can say sum, vocab sum, and mention its index. So this is going to return me the index of this position, index of this sum word. Okay, now whenever we are generating the output, okay, we will be generating the output in the format of an index. So for the future purpose, I'm going to create a variable that's called as vocabulary integer to word, and for this I'm going to create a small logic like this for c comma w in enumerate vocab underscore list, and I'll perform the dictionary comprehension like this, c colon w. So this will help me to convert the integer to word representation. Okay, now if I describe this vocab integer to word, this is what my Python dictionary is containing. So this is the index. Okay, this is the word to index and this is the index to word. Okay, now here I have created a Python dictionary that is called as vocabulary integer to word. So this is actually the index to word. Suppose if I have the index as 4697, so what is the word it is actually referring to? So previously this is a scenario of word to index, so I can get its index value. But if I want to get the index to word, so in order to do that, I'm going through my vocabulary Python dictionary that we have got above. So I'm going through each and every items. So I'm saying word comma C. So C dot index to W. So I'm just doing this integer to word representation. So once it's done, so previously we have seen that the sum index is 4697, right? So if I say vocabulary integer to word 4697, this will give me the output as sum. So that is what I have created in this variable. Okay, so this will help me at a later point in order to get the similar words to the word that I'm interested in. Now, once this is done, we can go ahead and work on the forward pass. In order to work on the forward pass, first I'll start by importing the NumPy as an NP. Then I'm going to define my one hot vector representation. So np.zeros here. My shape is, what is the shape? It is 1 comma my vocabulary length. Okay, my vocab length is the shape of my one hot encoder. Next, I'm going to write it like this, one hot. Okay, I'll write it as 0 comma vocab. Let's assume I'm interested in a specific word. I'm interested in a specific word that's mentioned as good. Okay, good is the word that I'm interested right now. So I'll get that particular word, and from there I'm going to access its index. On that index position, I'm going to set it equal to 1. So this is how I'll be representing my one hot representation for a specific word that is good. So this completes the first part that is on the left hand side. Instead of brown in our example, I'm considering the word as good. Next, what I have to do, I have to extract. Yes, I have to just go ahead and perform the dot product. Okay, I have to just go ahead and perform the dot product. So in order to do the same, I'm going to write it like this. I'll say Z projection is equal to np dot dot of my one hot representation, comma, my matrix, that is my word embedding matrix. So I'm just taking the matrix multiplication between my one hot representation and my word embedding. So this is going to result in the embedding of the word good. So if I describe the shape of my ZPROG, and it says that this is having the shape as 100, because see, this 100 is the shape of the word to vector representation of the word good. Next, what I have to do, I just have to go ahead and take the multiplication between my word embedding representation and my W out. Okay, that is what I have to do now. I just have to take the multiplication between W out and my Z that I have got right now. So in order to do the same, so I have to ensure that their shapes are matching. So I'm going to take the transpose of W out. So I can just write it like this. Okay, so we already have the Z projection that we have got. Now I'll store it in another variable called A projection, which I'll be using it at a later point. Okay, next here I'm going to write it like this. I'll say Z out is equal to np dot dot. Here I'm going to take the matrix multiplication between A projection, comma, W. What's the variable name that we have considered? Yes, it is W out. So it is W underscore out dot T to ensure that the sizes are compatible. Okay, now once this is done, I'm going to display the Z out dot shape. So Z out dot shape is having the shape as 1 comma 35561, which is this shape 1 comma 35561. So this is the outcome of the multiplication. Now what I'll have in the output layer, I have the softmax activation function. So which means in this scenario, I'll write it something like this. I'll say A out is equal to np.exp. I'm going to manually apply the formula for softmax, np.exp of Z out divided by np dot sum of np.exp of Z out. Okay, this is the output that I'm calling right here. Now if I describe the shape of this A out, it is still having the shape as 1,35561. Now what I'm interested in understanding as which are the words which are near neighboring words of the word good. So in order to do the same, I'm going to write it like this. First, I'm going to perform the flattening operation. I'll say a underscore out dot flatten. So this will perform the flattening operation. And then I'm going to write it like this. I'll say indices is equal to np dot arcsort, and I'm going to mention my A out. So this is going to sort in ascending order, but I'm interested in arranging in a descending order. In order to arrange it in a descending order, I can simply make use of the logic of the indexing. So indices colon colon minus 1, this will sort in descending order. Once it sorts in a descending order, the next thing that I'm going to do is I'm going to get the most likely context words. So for I in range 10, I'm going to mention like this. I'll say word index is equal to indices. I'll get that specific value over here. Then I'll get the integer representation of the word. I'll say this is the word vocab into word. Okay, I'll specify my word index. Okay, once I have this word index, I'm going to generate the output. So the way that I'll generate is I'll write as a out. So if I complete the score, so I'm getting the word as well as the score that I've got. So here it says the neighboring words for the word good are good sound, good bass, good quality, good high, good speaker, good build, mids, value, price, treble. See, you can correlate how the neighboring words of the word good. Okay, now if I want to repeat the same activity, let's say for bad, okay, if I do the same activity for bad, it is going to tell me, okay, what exactly is the like the words that are nearer to the words bad. So I've got bad news, bad, too bad, pretty bad, sound, bad boys, bad speaker. See, these are all the surrounding words of the word bad. Now you can check out and play around with the various values. So let's assume awesome. Okay, so for the word awesome, let's look into the surrounding words. Awesome speaker, awesome looks, awesome love, sound, awesome and awesome design, absolutely, really, super. So these are all the surrounding words. So what it means is after we have done the training, we have done with the experimentation, and what we have found is if I gave the word as the current word using the model that we have built, so it has shown what are the neighboring words that I have got. Okay, so that's the core intuition behind this implementation. So in this example, we have made use of skipgram model, and using this skipgram model, we have went a step ahead, and then using the skipgram model, we have found what are the context words from the center word that have got. And we were able to experiment it by training the model from scratch. All right, team. So with this, we come to the end of this video. So as part of our learning journey in this video, we have gone in depth and implemented the skipgram model and deepen our understanding by performing the forward pass with an example data. Now, as we progress in our upcoming video, we are going to look into the concept of continuous bag of words model in the word embedding. So I'll see you in the next video. In this video, we are going to learn about the technique that's called as continuous bag of words technique. Now, this continuous bag of words technique is an alternative to skipgram architecture that we have seen earlier. So let's get started and let's understand what exactly is this continuous bag of words technique. Now, as I mentioned, this continuous bag of words technique is an alternative to the architecture of the skipgram technique. Now, this continuous bag of words is a variant of this word-to-vec model. Now, what it does is it is going to essentially flip the overall dummy task around. Now, to help you get a clear understanding on this, let me just open the demo website. So this is the word-to-vec demo website that I have shown earlier. So I've got the same text that I had got earlier. That is, a quick brown fox jumped over the lazy dog. Now this time I'm going to select as continuous bag of words. So that's the variant that I have selected right now. Now with the window size as 2, now if I generate the data set, the way that I have generated the data is completely different. So this time I'm interested in finding the middle term given the context window. So here, given all the words that I've got in the context, excluding the middle one, what is the most likely the word at the center? So as a result of this, so I've got the A as the output and the word quick and brown as the input. So interestingly, if I observe the output for brown, okay, for the output for brown, so the inputs are a quick fox jumped. So this is my input. So this is the input with my sliding window size of 2. So given the words a quick fox jumped, I want to predict the output, that is brown. Now given the input as quick brown jumped over, I want to predict the output as fox. So this is how my training examples will be changed. So as you can clearly see, my training example, the way my training example or my input is structured is completely different than what we have seen earlier when we talked about the skipgram approach. So which means if I talk about my model architecture, even in this scenario, the input of my neural network has to have an ability to specify the multiple words instead of one hot vector as an input. Now in such scenarios, what we will have over here is, in this scenario of this continuous bag of words approach, so we are going to have a bag of words approach. That means I'm going to have a bag of words. I'll have a bag of words vector. It's the same concept, except I'm going to put one in the multiple position. So this is like the bag of words approach with binary as true. If you remember in the last section, when we have implemented this bag of words technique, I have shown you with binary as true, right? So this is the same way. So irrespective of the number of times the particular word has occurred in a document, I'm just going to consider as whether that particular word is present or not. So that's the bag of words representation. Let's suppose if I've got the 10,000 words in my vocabulary, then my input will be of the shape 10,000. Now my inputs are, let's say, quick, and let's take up the example, quick brown jumped over. So in such scenarios, for corresponding to each and every word, I'll have it as 1 present over here. So in this way, we are going to have the input vector represented. So this is the bag of words representation. In the output layer, so it would still be the same. So assuming that 10,000 is the number of words that I've got as a vocabulary, so I'll have the vector of the shape 10,000, but this time I'll have the softmax activation function. And in the hidden layer, it's the same thing. In the scenario of this hidden layer, we are going to have, let's say, 300 neuron. So this 300 represents the number of columns or the number of features in the matrix. Okay, along the rows, I'll have the each row corresponding to the vector representation of my individual words. Okay, so this is how the data would look like. Now, with my window size as 2, so the skipgram was actually generating up to 4 training samples per center word. But in this scenario, the continuous bag of words, one thing that we can see is it is going to generate only 1. Okay, now with the skipgram, we actually saw that by multiplying a one hot encoder, that is the one hot vector, it is going to select a row from my hidden layer. But this time, when we multiply a bag of words vector, so the result is the corresponding rows, and like it is going to perform the sum of the corresponding rows. To help you get a clarity on this, let's say I have a very small vector which has the vector representation like this 1 0 0 1, and I've got a word embedding matrix which has the values as 15, 16, 10, 20, 30, 4, 5, 6, 8, and 10, 11, 12. So this is of the shape 1 comma 4. This is of the shape 4 comma 3. If I do the multiplication, it will be 1 comma 3. But this time, since I've got 1 in both the places, so as a result of applying this matrix multiplication, so this is nothing but, so 1 into 15 plus 1 into 10. Then for the second term, it will be 16 plus 11. I'll directly mention the output team. So 15 plus 10 is 25. 16 plus 11 is 27. 10 plus 12 is 22. So in this way, I will be performing the sum. So for this continuous bag of words architecture, so what we do is we are also going to divide this sum by the number of context words in order to calculate their average word vector. So by doing like this, the output of the hidden layer in my continuous bag of words architecture is the average of all the context word vectors. Okay, so this is the only difference between my continuous bag of words approach and the skipgram approach. In place of continuous bag of words, I'm going to have my input data represented in the format of bag of words representation. So with this bag of words representation, we'll be performing the sum. And finally, we'll have the output layer, which is very similar to the one that is last time. Now coming to the practical implementation. So I'll come to the notebook. This is the notebook where we have performed the skipgram implementation, right? So in order to do the continuous bag of words implementation, while defining the model, we just have to mention skipgram as 0. So this is going to take the continuous bag of words approach. And the rest everything is the same. If I come at the end, so if I apply the skipgram, if I apply this overall continuous bag of words approach, and if I check for the word, let's say in this example, awesome. So it says ops absolutely looks super, sound, thank, value, wow, price, service. So these are the words which are near to the words according to the word awesome as an input. Okay, so this is how we can go ahead and implement the continuous bag of words instead of skipgram approach. Coming to the practical implementation, it's very simple change, but coming to the model architecture, it's little different. So it's very important that you understand why do we say CBOW, that is why do we use the term of continuous bag of words. The reason that we use this term as continuous bag of words because instead of one hot representation, we have the bag of words representation in the input. So with this, we come to the end of this video, team. So as we proceed in the upcoming video journey, we are going to look into the hyperparameter tuning in the word-to-vec model. So I'll see you next time. Welcome back to your learning journey. Now in this video, we'll talk about the hyperparameters that are involved in the skipgram word embedding model. So as we proceed in this video, we are going to learn about the technique of subsampling as well as the concept of negative sampling. So let's get started, and let's start by understanding this subsampling and why it is required. So before that, let's consider back our data, that is the skipgram data that we were working with. Now in the example that we were actually discussing, so the data set had 10,000 vocabularies. Now with 10,000 vocabularies and 300 as the components, then in such scenarios, if you consider our neural network, this is going to have the word embedding matrix will have 3 million weights each. See, it's not just one matrix, it will also be present in the two matrices as well. One is the hidden layer and the other one is the output layer, which is what we have seen when we were experimenting with the help of forward pass as well. So In the example that we had, where word vectors were having the 300 components with the vocabulary of 10,000, then in such scenarios, we were having this 3 million weights each. Now, assuming that I've got the 3 million weights each, now think about training such complex neural network. Obviously, if I'm running a gradient descent technique with the help of this neural network, it will be taking a lot of time. Hence, I can clearly say that the training will be very slow. And to make this matter worse, we also had huge amount of training data in order to tune so many weights. The reason that I'm saying that we'll have too many data, because if you remember in the last session, when I have shown you an example of word to vec model, suppose if I have got 10 words over here, okay, depending on my window size, I'll be generating multiple pairs. I'll be generating multiple training pairs. So this would also result in overfitting. So millions of wait times, billions of training examples means this is going to perform at the very worst. So that's one of the bad thing in this scenario of the skipgram technique. But when we have implemented it with the help of the GenSim model, we were able to implement it quite fine, isn't it? Which means something has happened in the background which ensured that we were able to get this an optimized result. So what has happened in whenever we are training was, so the authors of this word to vec approach, that is the word to vec model, they have applied a sampling technique. So what they are going to do is they'll perform the activity of subsampling. Now you can refer this research paper for the complete information about the same. But if I want to give you an overall idea from the summary perspective, so they are going to subsample the frequent words in order to decrease the number of training examples. So the context window is actually shrunk by random amounts to give the greater weights to the clear context words, and they also modified the optimization objective with a technique which they actually called it as negative sampling. So let's understand in detail about this negative sampling and the subsampling. So here, when we say subsampling, okay, so before I take you through this subsampling example, so this is the pictorial representation of our training data set. Okay, so here as part of your slide, you can clearly observe that this describes some of the training samples that we have got. So training samples is nothing but the word pairs. So we are going to consider them from this sentence. The sentence that I've got is the quick brown fox jumps over the lazy dog. Now for the demonstration purpose, I've just used the window size as 2 in this example. Now with the window size as 2, these are my training samples. Now if you look into this scenario, especially the training samples that I've generated, here I've got the word pair of, let's say, the quick or the fox. So I can have many such pairs that is possible. Let's suppose I'm having a word pair as fox the. So when I have the stop word like the present along with the word like fox, then in such scenarios, so what it clearly means is I'll just have more information about the stop words than the representation for the important word that I've got with me. So in order to address these kind of issues, what we are going to do is we are going to implement a scheme that's called as subsampling scheme. So for each word we encounter in the training text, we are going to assign a probability, or we can say that there is a chance that we are going to effectively delete it from the given text. So the probability that we cut the word is actually related to the frequency of occurrence of the word. Suppose if I have a window size of 10, then in such scenarios, I'm going to remove the specific instances of the word the, which could be a stop word from my text. And as I train with the remaining words, the word the will not appear in any of the context windows. So as a result of this, I will have less than trained examples where the word the is present. Okay, so this is the overall idea about this subsampling. So for each of the word that we encounter in our training data, there's a chance that we will effectively delete it from the text on the basis of frequency of its occurrence. So this will help me to reduce the training sample size, thereby decreasing the effect of the stop words, the words which do not add much context for the given text data. Now you can check the documentation page as well as the research paper for the sampling rate formula. The original implementation was in C programming language. You can check out the same. So there are actually the formula which is mentioned over there, which helps us to specify the value for probability. Okay, so that's the overall concept behind this subsampling technique. Now, apart from this subsampling technique, so the research paper also talks about the context position weighting. Okay, concept context position weighting. Now here, this word to vec model effectively weights the context words differently based on their position within the context window. So specifically speaking, the context words which are nearer to my center word, they should be given more weightage compared to the words which is farther away from the center word. Now, this intuition is not actually implemented in the math or an architecture of the neural network. So instead, this weightage is actually achieved by randomly shrinking the size of the context window. So that's a very small idea behind this context position weightage. To give you an example, suppose if I've got the center word as brown, then I'll be giving more weightage to the nearer words like quick and fox compared to the words of jumps and the. That's the overall idea behind this context position weightage. Okay. Now, apart from this, there's another technique the authors have implemented that's called as a negative sampling technique. Now, when I say negative sampling technique, it's about the converting the task that we have got at hand, that is the language modeling task, into a binary classification task. And this we do it by generating a new negative samples from the data set. Now, in order to understand the same, let me open up my OneNote to help you understand this concept. Okay, now if we talk about the general scenario of the language modeling, that is generation of word embeddings. So what is the task that we are dealing with right now? Currently, we are dealing with the task by sending in the input and the output pair. So in the output, I'll have a word, let's say quick. Okay, I'm going to send it to my model and I would expect my model to predict the next word. Let's say the nearest word for this word quick will be brown. Now in this scenario, when I'm using the model, so first thing the system has to do, even what we have seen in the scenario of this as well, is first the system has to get the word embeddings. So once it gets the word embeddings, it has to calculate the prediction. So once it calculates the prediction, we are going to project the output vocabulary, and finally we are going to decide as what is the overall output for the vocabulary. So these are the steps that will be performed whenever I'm generating the prediction. So when I'm generating the prediction on a trained model, so I'll use a data, I'll generate its word embedding, I'll calculate the prediction, and I'll project my output vocabulary. Now, if you look into this third step, that is projecting my output vocabulary, so this is a step which takes a lot of computation. Here, in this scenario, just imagine I've got the entire data set containing, let's say, million of data, like let's say 1 million rows that I've got in my data set. Now, if I want to run this computationally intensive task on this millions of data, obviously this is going to become a bottleneck to us in the performance. So as a result of this, so what we do is we are going to do a specific activity. So in this scenario, what we will be doing is we are going to think in generating the high quality word embeddings. So we will go ahead and generate the word embeddings, which is an high quality one. So let's see how we can generate a high quality word embeddings. So in order to generate this high quality embeddings, so what we are going to do is instead of predicting the neighboring words from the current word, see in my current word I've got the quick, so I'll send it for my word embedding. Okay, and using this word embedding model I'm going to predict the neighboring word. So neighboring word is brown. So instead of predicting this neighboring word, what I'm going to do is I'm going to switch to a model which takes both input and output. Okay, an example can be something like this. It takes both the words, that is quick, and its nearby term, that is brown. Then what this model is going to do is this model is going to tell me whether they are neighbors or not. So in this scenario, obviously quick and brown words are neighboring words. So I'm going to get a highest probability scores. So I'll get the output as 0.95. So what it says is I'll specify an input and output word together for my model, and this is going to generate the output between the values of 0 to 1. The value closer to 0, it indicates that these words are not neighboring words, and the value closer to 1 indicate that these words are actually neighboring words. Now with this simple switch, we don't have to go ahead with the complex implementation, the computationally intensive implementation that we had earlier. Instead, we are directly applying this logistic regression model. We are directly applying this logistic regression based model. So as a result of this, this became much simpler. So that's one of the best part when it comes to switching the task. Now the question is, how can I get this data? Well, we'll get the data in the same way that we have got last time. So this is an example that we have seen earlier. Let's say the quick brown fox, lazy dog. Now in this scenario, I'll select the skipgram with the window size as 2, and if I generate this data, see this pair, that is the quick, the brown, quick, the, we have got the input and output pair is there, right? So we'll send this both input and output pair to this logistic regression model. And this logistic regression model is going to tell me whether they are actually closer together or not. That is whether these two words are neighboring words or not. Which means for each of the training pair that I have got over here, see, for each of the training pair, so in this example, for each of the training pair, I'll have the label as 1. Okay, I'll have the label as 1 for each of the training pair that I have got over here, which I've generated from the skipgram approach. So this input and output both will be sent as X, and Y will be my target. Okay, so with this features on the target, I'll be training this linear regression model. Now the target says whether these two words are neighboring words or not. Obviously they are the neighboring words because these are the pair of words that I have got from the window size. Now obviously with this approach we will have a computationally faster. The implementation will be pretty much faster. As a result of this, we can process millions of examples in a matter of seconds. But the problem is the overfit. See, in this example, I've generated a data set, and in my entire data set, the entire data belongs to the target as 1. Now, if I have the data which is biased towards a specific class, then in such scenarios, that's a model cannot generalize the given data set. So this is going to lead to overfitting. Now, in order to avoid the overfitting, what we are going to do is we are going to introduce a negative samples. So we will introduce the negative samples. Now with this negative samples, what it means is we are going to consider the data. Let's say I'll consider the word the. Okay, I already have the word quick. Next, what I'm going to do is I'm going to add some more examples which has the target value as 0. So whatever the words that I've got in my vocabulary, let's say in my vocabulary I've got 500 words. Okay, so out of 500 words, for the word the, there is the output as quick. Now what I'll do is I'm going to pick up the random words from the vocabulary and I'll make the overall target as 0. Let's say I'll mention the and then lazy. I'll say it as 0. The cool, 0. So these are the examples that I've generated, which we call it as a negative samples. So these are called as the negative samples or the negative examples. So we'll consider the correct pair from the training data that I've generated, and I'm also going to generate the negative examples. While generating the examples, so I'm going to consider the output word by selecting the words in a random manner. Now, as a result of this, we are going to have both the rows belonging to the class as 1. Along with that, we'll also have the rows belonging to the class of 0. So this would overall lead to a great trade-off between the computational as well as the statistical efficiency. So we combine the skipgram with the negative sampling approach, and then we are going to perform the training so that we are able to perform this activity in a much more effective way. Now, to help you understand how the training process is going to happen in the scenario of the negative sampling. So what we are going to do is, in this scenario, I've got two inputs. One is input and the another one is the output, and the other one is called as the target. Okay, so input and output are the training samples that I've got. In this example, the quick, the brown, quick, the quick brown, and so on. So in this scenario, what we are going to do is, before the training process is going to start, so obviously whatever the text data that I've got, I'm going to pre-process this text data. Now in this step, I'm going to determine the size of the vocabulary. Okay, which means I'll decide how many number of words that I want to keep in my vocabulary, as well as what will be the dimension of my word embedding vector. So let's take up an example. Let's say I have got a matrix. Okay, this matrix is like this. Okay, and I've decided that there will be 10,000 words in my vocabulary. So I will have 10,000 rows. This will be my vocabulary size. And along the columns, I'm going to define the embedding size. So for the embedding size, we'll normally keep it as 300. So 300 being a common value. Okay, I'll have my embedding matrix size of 10,000, 300. Now with this embedding matrix size, what we generally do is, during this training phase, I'm going to create two matrices. One matrix is my embedding matrix. The another matrix I'm going to define, it will have the same shape as my vocabulary, obviously 10,000, and the size of my embedding as well, that is 300. And this will also having the same size, and we call this as a context matrix. Okay, we will have two matrices, context matrix and the embedding matrix. So these two matrices have an embedding for each word which are present in my vocabulary. Okay, so my vocabulary size will be the number of rows in this matrix dimension, and we'll have the number of columns equal to my embedding size. Now at the beginning of the training process, obviously I'll be initializing this entire matrix to some random values. Then that is when we'll start doing the training process. So in each training step, I'm going to take one positive example and its associated negative examples. In this scenario, I'll consider the first row. Along with that, I'll also consider the associated negative examples. Now, once I consider these words, okay, next what I'm going to do is I'll go ahead and get the embedding. Okay, I'll go ahead and I'll get the embedding. So for my input, I have the word the, isn't it? So from my embedding, I'm going to select the row which refers to the word the. Okay, this is the embedding for my input word. Then what I'll be doing is, like, the next thing that I'll do is in the context word, I'm going to look in my context matrix, that is over here. Okay, then in this context matrix, I'm going to get the word representation for the other words. So the other words context representation are quick, lazy, cool. So this is the quick, this is my lazy, and let's say this is my cool. Okay, I'll take the context or the embedding representation in the context matrix for the words that I have got in the output. Next, what I'm going to do is I'll just go ahead and I'll take the dot product between my input word and the output word. So I'll take the dot product between the word embeddings of the with the word embeddings of the word quick, word embeddings of the word lazy. Okay, I'll say the dotted with quick, the dotted with lazy, okay, the dotted with cool. Now, obviously, this is going to result in a numerical value. So let's say I'll get the numerical value as 0.8 minus 0.7, let's say 0. Okay, these are the outputs that I'm getting right here as a numerical values. Now, along with that, I also have a target. Okay, this is my output, kind of an output, and this is my target. My target is, let's say this is 1, 0, 0. Okay, now the expectation is I should be having an output closer to the target. In this scenario, I'm getting the real values. So if I have a real values and if I want to convert it into a binary problem, then I can directly apply a logistic regression model. So when I say logistic function or a sigmoid function, so this is going to generate the output in the range of 0 to 1. So as a result of this, if I apply sigma, that is the sigmoid function on this output, I'll get the output, let's say 0.8, 0.1, okay, 0.1. Okay, so this is the output that I would get. So as we can clearly see right now, as a result of applying my sigmoid activation, so for the dot product between the and quick, I'm getting the output as 0.8, but the target is 1. So in this way, I'll find the values of target and the prediction. Now once I have these values, the next thing that I'll do is I'll go ahead and I'll calculate the error. So error is 0.2, 0.1 and 0.1. So this is the value of error. It's the difference between my target and the output that I'm getting. Next, with this value of error, we'll then go ahead and apply the back propagation, and we are going to update the overall model parameters. So when I say updating the model parameters, it's nothing but the updation. Okay, it's the updation of these values, that is the context vector representation as well as the word embedding representation. So in this way, we will be doing the update in a much more effective way. Okay, so that's the core principle behind this negative sampling technique. So the number of negative samples that we are going to consider, as well as the window size that we specify during the skipgram approach, these two are the hyperparameters of this skipgram model training approach. All right, team. So with this, we come to the end of this video. So as part of your learning journey in this video, you have seen the overall idea and the complexities behind the skipgram approach, the key concept behind this subsampling technique, and at the end, we have also looked into the technique of negative sampling. In the next video, we are going to look into the difference between the skipgram approach and the continuous bag of words approach. So I'll see you in the next video. In this video, let's look into the difference between the skipgram approach and the continuous bag of words approach. Now, when you compare both skipgram and the continuous bag of words approach, one major difference that you would generally observe is that when you're working with the skipgram approach, in that scenario, we are going to generate more training samples or that more training examples compared to the continuous bag of words approach. Now, in the scenario of the skipgram approach, The number of samples in the skipgram is dependent on my window size. But if you consider the continuous bag of words, so we'll only have one sample per word. Now, as a result of this, we are going to note down some of the key practical differences. One thing that we can observe is skipgram takes much longer time in order to train. And if I have a very large window size, then in such scenarios, this is going to increase the training examples. Hence, it will take much longer to train the model. And along with that, the skipgram may perform better whenever we have got the training data set which is very small, because in this scenario, it can generate more data for training purpose. In other words, this holds true for the other scenario as well. Whenever I've got the rare words in my given data set, in such scenarios, the skipgram creates better representation for those rare words. The reason is we are going to generate more training examples, even though that's a rare word. It will be present in multiple training samples, which in turn helps us to have a better representation of those rare words. And some of the key points that you need to know about this continuous bag of words approaches, this continuous bag of words performs slightly better than the skipgram approach, especially when it comes to capturing the syntactic relationships. So this is because in my input, I'll be having the continuous bag of words. And continuous bag of words performs slightly better whenever we are having a more frequent words. So this is the major difference between the skipgram approach and the continuous bag of words approach. So with this overall learning journey, you have a clear understanding of this word-to-vec model in depth. Now, as we proceed in the next video, I'm going to have a bonus announcement for you. So in the next video, I'll teach you as how parameters are actually updated during the backpropagation. In the earlier part, I have described as how does the forward pass is going to happen, isn't it? Now in the next video, I'll give you an intuition as how does the backpropagation is going to happen. Now while explaining this backpropagation, I'll also make use of the negative sampling examples as well. Now using this negative sampling, we are going to implement it and understand in a better way. So I'll see you in the next video. Hey everyone, welcome back to your bonus video. Now in this video, we'll go into the more depth on the word-to-vec model training. And here, I'll walk you through some examples and I'll show you the specific steps that we have to take in order to update the weights whenever we are training this word-to-vec model. Okay, so here this overall information that I'm going to share it with you, it's based on the research paper that was published by the Google. So please go ahead and refer that research paper. So let's get started. So first thing that you have to remember whenever we are working with this video is we'll start by defining our matrix names. So here when we are training our word embeddings, okay, so we will be giving the input with the help of this one hot encoding, and then this will be sent to my weight matrix, that is my word embedding, and then we'll also have some another matrix that is my output layer matrix, and then we'll have an output layer. So we have got the input layer, which is my one hot vector, and we have got the hidden layer, which is my weight matrix, and an output layer, which is my output layer weight matrix. Now, for the sake of simplicity, I'm going to call two things. I'll just refer it as input matrix. Okay, I'll consider only two things as of now. I'll only consider my input matrix and my output matrix. So these are the two things that I would consider as of now. Now I'm not going to use the terms of neurons anymore because it will help us to understand the concept much more in a better manner if I use these terms of input matrix and the output matrix. This input matrix is our word vector table, which is nothing but the word embeddings matrix. Now this word embeddings matrix, if I show it to you in a pictorial format, this is the pictorial representation of my word embedding matrix. So this word embedding matrix will have one row per word of my vocabulary. Okay, and the number of columns in this word embedding matrix is referring to the dimensions of the embedding vector. Okay, and we are going to have the output matrix. This output matrix is of the same size. Okay, so this output matrix is of the same size, which is nothing but the number of rows, which is equal to the length of my vocabulary and the number of dimensions that I want to have on my word embedding. Okay, so both of this input matrix and the output matrix will have the same shape. And then here in this scenario, we will have the activation function at the output layer. So in my output layer, we will have the activation function, that is our softmax activation function. So the reason that we are going to have this softmax activation function, because I want to generate the output in the format of a probability score. Here, the overall goal for me is to find out the nearby words. Okay, I want to find out my nearby words. So when I'm doing the forward pass, I'm going to send a word as an input and I'll be expecting the nearest word to me. That's the overall idea when I say an output layer of softmax. Okay, so this is the overall idea when we are talking about the model training approach. Now, apart from this basic understanding, in the last video, I have talked about the skipgram. So I have talked about the skipgram model parameters, and I've also talked about the concept of negative sampling. Now, in the scenario of this negative sampling, so what we are going to do is, instead of performing the activity of finding the nearby words, what we are going to do is we are going to use our input and output pair that I've got, and I'm going to train a classifier. Now while training my classifier, I'm going to include the negative samples. So these negative samples, we actually get it from my randomly selected words from my vocabulary. Now that's the core principle behind this negative sampling technique. Now skipgram and the negative sampling technique is the core principle behind the training of this word-to-vec model. So let's understand how it actually works. Now let's talk about the initial weight values. Now when we are working with this skipgram approach with the negative sampling, so what we are going to have as part of our training data. So here, as part of our training data, in the scenario of this skipgram approach with our training negative sampling, so I'm going to have my input, I'll also have an output, and apart from that I will also have the target. So input and output, the words that I've generated. So for the words that are present in my given data set, let's say I have the words as good and job. I'll have the output as 1 because job is a nearby word for the word good. Let's say good dummy. It's some random word which is a negative sample. I'll have the target as 0. And when I say good boy, okay, I'll have the output as 0, assuming that this combination is not at all present. Okay, good key, I'll have the output as 0. So these three samples are my negative samples that I've generated from the given vocabulary, and this is the positive sample which is from my data set that I have generated. Now when we are working with these kind of data, so at the beginning, okay, at the very beginning, all the weights that I'm going to have in my output matrix, okay, all the weights that I'll have in my output matrix, it will be set to 0. And all the weights that I'll be having on my input matrix, so input matrix is this. So for this input matrix, the weights will be the random values. So this will be the random values and this will be set to 0. So in this scenario, with this skipgram and negative sampling approach, we have just changed the input and the output, but the size of the matrices would stay the same. So this we have discussed in the previous video. So my input word embeddings will have the random values. My output values, that is my output matrix, will be set to 0. Okay, so this is the overall scenario that we have got. Now Let's start with the forward pass. So here I'll begin with the positive sample, that is good and job. So good is an input and the nearby word for the good is job. So the positive sample that I've got with me is good and job. Now if I want to perform the back propagation, first I have to perform the forward pass on the neural network. So in order to do this, I'm going to select the vector representation of the word good, and then I'm going to select the vector representation of the word job. Okay, so this I'll get the vector representation from my input matrix, and the vector representation for the job I'll get it from my output matrix. Once I have the vector representation of the same, I'm going to take the dot product. Okay, I'll take the dot product between these two vectors. Now once I apply the dot product, the next thing that I'm going to do is I'm going to apply an activation function. Okay, I'm going to apply an activation function. Now let's assume I've got a network, and this network is trained very well. Now if this is my training sample, that is my positive sample, then for the positive sample scenario, I'm going to have the word that is good will be much more nearest for the word job. So as a result of this, when I apply an activation function, since we have got the sigmoid as an activation function this time, okay, since it's a binary classification, I'll have a sigmoid as an activation function. Now in this scenario for the sigmoid activation function, let's say I'll get the output closer to 1, 0.995. So which means the word good is nearest for the word job. So this is how we are going to get the overall output. Now remember, I want to mention an important point over here. Whatever the output that I'm going to get, that is 0.995, it is not a similarity measure. I'll repeat here because many of my learners gets confused on this scenario. This is not a similarity measure. So instead, what it describes is it describes the nearby. Okay, it describes whether this word is nearby to the word that I am present. It is like specifying whether the word job, whether it is in vicinity of the word good. So that is what it clearly describes. So it can be a scenario where my word good and job might not be similar together, but they are they could be actually like present, or they could be one near to the other. So that's the overall idea, team, because job would mean something different, good would mean something different. But here I'm talking about vicinity, whether they are near or not. Okay, once I perform this activity, that means once I find the value of output 0.995 is the y hat, that is my predicted output. Now once I have the value of the output, the next thing that I'm going to do is I'm going to calculate the value of error. Now before I take you through the error values and everything, I'll take a pause over here and let me show you some of the other examples as how does the sigmoid output would look like whenever a particular word is not in vicinity of my current word. So I'm going to explain this with the help of a table. Here I've got a table which describes what is the word for my input and what is the word for my output and what is the output of my activation function. Okay, that is what I'm going to specify right now. And along with that, that table also describes the value of error. So here in this scenario, for now, just observe the table that we have got. So here I've got input, output, activation. I have mentioned that for the word in this example, I think the table describes the word between done and job. So if I've got the word done and if I've got the word job in this table example, I've got the output of the activation function as 0.9957, which means this is my positive sample. So for the positive sample, the output from my activation is 0.9957. And for the other samples that I've got, so these are the negative samples. So since it's a negative sample, if you look into the output from my activation function, see, it clearly says what exactly is the output from my activation function. It also says done and can is having the output as 0.8567, assuming that that is also a valid combination. So let's say first one is the positive sample and the next three are my negative sample. So that is what we have that I can specify from this given data. Now, one thing that you can observe right now is the output of my activation function for the positive sample is closer to 1 and the output for the negative sample is closer to 0. So that's the core principle that we have learned. Now, once I perform this forward pass, so this activation function is nothing but the value of output, that is my forward pass. The next thing that we do is we are going to calculate the error. So what is error? Error is given by difference between y and y hat. Now this is my y hat. Let's say my y is given by 1, 0, 0, 0 like this. So I've got the values of 1 like this. Now with the values of ones and zeros for the first four rows, which we are clearly interested in, I'll take the value of difference, that is the error. So if I take the y minus y hat, so this will be 0.0043. Okay. Now this is the error that I'm going to get, that is y minus y hat. Now once I do this activity, okay, so once I do this activity of computing the error, so here for the simplicity of working, let's assume I'm also going to multiply it with the help of the learning rate. Let's say I'm using the value of learning rate as 0.025. So if I multiply 0.0425 with 0.0043, I'm going to get the value of error as 0.0001. Okay. In the same way, if I take the difference between 0.0987 and then multiply it with 0.025, this is the output I'll get. So likewise, so I have found the values of error in this way. Okay. I have taken the difference between the expected output and the predicted values and I have multiplied with my learning rate in order to arrive at the error value. So in this example, I have considered the learning rate as 0.025. So this is an hyperparameter. So which is very similar to what you are aware of whenever we are training the neural network. Okay. Now, once I've got the values of error, the next important step is the updation of the weights. So we have got the values of error. The next thing is update the weights. So how do we update the weights? Now, this is a very important activity. Now, in order to update the weights, let's say I want to update the weights of the word job. Okay. So first, when we are updating the weights, we have got two weight matrices. One is my output matrix, which is my context embedding, and the other one we have got is the input matrix, which is my word embeddings. Okay, so if I want to update my output matrix, so I'm going to consider the updation of my output matrix. If I want to update the output matrix, so in the output matrix I've got the word job. Okay, that's the word that I have got over here, that is job. So if I want to update the word for job, so I have to take the input vector for the word that I have got. In this scenario, the input vector is done. Okay, once I get the input vector as done, I'll have to multiply it by the error value that we have got, and this is going to give us the value of gradient for the output weights. So if I want to mathematically represent this, I'm going to write it like this. So I've got my output matrix. So if I simply display only the values of my output matrix, it would look like this. So in my output matrix, I've got the word job, stop, inhibited, want, can, and bajrang. Okay, these are the words that are present in my output matrix. Now what I'm going to do is, whatever the error value that I have got over there from the table, Okay, so from the table, I've got the error value over here as 0.0001. Okay, so what I'm going to do is like output. So when I say output matrix, that is a vector representation of job. So this is equal to 0.0001 times my input vector. That is the vector representation of the word done. In the same way, okay, so in the same way, the word stop will be updated as, what is the value of error that we have got over here? It is minus 0.0025. Minus 0.0025 with input vector representation. So in order to update the output weights, let's say for the word job, I'm going to take the input vector for the word done and I'll multiply it with the error term, in this scenario 0.001, and this is going to give us the value of gradient. This is the value of my gradient. Now with this value of gradient, I'm going to update my output with the help of the formula. Output is equal to output plus the value of gradient. So as you know, gradient is a term that we use it to refer as how much value or how much quantity of update that I have to make for my weights. Okay, so this is the core principle when it comes to updation of my output matrix. In the same way, if I have to update my inputs, okay, obviously, so when I'm coming in a backward way, first I'll be updating my output matrix and then this will be followed by input weights, right? That is my input matrix. So in order to update this input matrix, so it's a little different. So obviously, in case of my updation of my inputs, so I only have one input. So the one input is done. Okay, so I'll have the vector representation of the done, and the way that I'll be updating is I will say plus or minus. Okay, plus or minus, I'll plus equal to, it's not plus or minus, it's actually plus equal to gradient. So here I'm going to find the value of gradient by summing up the entire value. So what is the entire values? By summing up of values of error times my output vector. Okay, error times the output vector, which means I'm going to multiply the error values. So this is the pictorial representation of the gradient computation for the input weights update. So I'm going to multiply the error with my vector representation of my output, that is job, and I'll do the same thing for each and every output and the error value. I'm going to sum it up. If I do the summation, that will give me the value of gradient. Now with this value of gradient, I'll be updating the input weights as done is equal to, that is the vector representation of the word done is equal to done plus gradient. So this is how I'll be updating the parameters of my input word. Okay, so in this way, we will go ahead and update the parameters. Now, once we update the parameters, we will go ahead and continue to do the activity and we'll perform the forward pass, backward pass, and we'll do it as per our requirement until we get the required output. Now, in the given scenario, so I'll continue to do this activity until I have reached a point where only on a specific scenario I have it as 1, rest everything it is 0. So maybe an ideal scenario would look something like this. Okay, so here this is the values of my previous activation and this is the values of my new activation. So in this scenario, we had a large incorrect value. So as a result of this, we had a large error value. And now after the update, you can clearly observe this value is actually closer to 0, which means that, so this is an example of negative sample. Okay, this is a negative sample example. So this table clearly proves that whatever the update that we have performed, so it has updated in a right manner. You can go ahead and try to implement it from your side as well by referring to the program codes that are shared by the experts in the C programming. So it will be a fun if you, in case if you want to experiment it. So I done this a very long time for the research purpose. So you can continue to do at your own pace as well. So the key takeaway from this video is whenever I'm doing the training. Okay, whenever I'm doing the training, first thing is, so if I'm using the skip gram and the negative sampling approach, I'll have input and output. Both input and output will have its own matrices, input matrix and the output matrix, and the target will be whether they are near together or not, and we'll perform the forward pass. And in the output layer, in this example, we'll have a sigmoid activation function since we are also dealing with negative sampling. Then we'll calculate the value of error. Once I calculate the value of error, to update the values, this is the formula that I'm going to apply for updating the output matrix. Once I update my output matrix, I'm going to update my input matrix. Okay, so this is the overall way in which we are going to perform the forward pass and the backward pass whenever we are training this word-to-vec model. I hope you have got an in-depth understanding of the same. So thank you so much for watching, and I'll see you in the next video. In this video, let's look into the summary of our learning journey that we had till now. So as part of your learning journey till now, you're now aware of various techniques in order to represent the text data. So we started with the basic approaches to the state-of-the-art deep learning based methods, which includes the word embeddings. Now, let me reiterate one important thing. There's no single approach that fits all for the given test data. So the best approach for the given text data is all the one that is going to depend on the domain that you're working and the data that you're working with. So with this, I conclude this section. So in the next video, we will look into the end-to-end pipeline for text classification. Welcome back to your learning journey of natural language processing. Now in this section, we will look into the end-to-end pipeline for text classification. Now, as you know, in today's world, one of the biggest sources of the information is the text data, which is highly unstructured in nature. Now, the use cases can be finding the customer sentiments from the product reviews or feedbacks, or extracting the opinions from the social media. So these are some of the examples and the use cases of text analytics. Now, as we progress in today's session, we will look into the reality of text data and we will understand what exactly is this text classification. We will look into the examples of text classification, and at the end, we will look into a general pipeline in order to perform this text classification. So let's get started. Now, if you think about it in a real life, all of us check the email each and every day, multiple times of the day. One of the amazing feature which is provided by email providers are the ability to automatically classify the emails into spam emails along with the unnecessary emails. So it will help us to separate the spam email from the non-spam email, isn't it? So here, classifying the emails into a spam email and a non-spam email is one of the famous tasks of text classification. So this task is focused is this task is actually focused about whenever we receive any new email, we want to actually check whether it belongs to a spam or whether it belongs to a non-spam. But the problem is it's very difficult to extract the value from this data unless it is organized in a certain way. And here we have to find the various methodology to extract the value from this highly structured data. And till now, you have already learned the various methodology to extract the value from that data. So after we apply those methodology on the text data, then we can use it for further processing. And another challenge that we have whenever we are working with the text data is analyzing and bringing the value from the text data is a time consuming task. And also, if I have got a very large text data, classifying it whether it is a positive one or a negative class, that is one of the another challenge that we currently have. So that's where the text classifier comes to the rescue. The text classifier helps us to structure the text data in a fast, cost-effective and a scalable manner. So let's understand what exactly is this text classification. Well, when I say text classification is also known as text tagging or text categorization, which is a process of categorizing the text into the organized groups. Here, with the help of the NLP techniques, the text classifier can analyze the text and assign the set of predefined tags or categories based on its content. And this has got the application in chatbot as well, which you will be learning in future sections. To give you an example, so in the scenario of text classification, we will have an input text data. The input text data can be something like this. Movie is amazing. So this is my input text data. So here I'll take this text data, I'll perform the pre-processing, convert it into a numerical format and extract the value from this text data. And then I'm going to assign a label for this given text data. That means whether it is a positive or whether it is a negative sentiment. So this is an example of text classification, and the machine learning model which we have built this to perform this task of text classification is known as text classifier. So that is the overall idea about this text classification. Now this has the multiple applications. To give you an example, it is used in sentiment analysis. So here, when I say sentiment analysis, it's about the task of understanding if a given text is talking positively or negatively about a given subject. And the another task that we can generally use over here is topic detection. Here, this is actually a task of identifying the theme or a topic of a piece of text. And the another example for text classification is language detection. So this is a task or a procedure of detecting what exactly is the language of a given text data. Now to give you a real-time example, let's do one thing. Let's go to the Google search. Okay, I'll open the Google Translate. So if I open the Google Translate, so let me just pick it as detect language. Now when I say detect language, and if I mention something in English language, I'm going to mention something like this. I'll say, how are you? So when I say how are you, currently the language has been detected as English. So this is how a language detection model is going to work. What it has done is, by considering my input text data, it has assigned one of the classes that is available in this list. Okay, so this is an application of text classification, which is the language detection. All right. Now, apart from this text classification, which we have seen that is the language detection task, we have various tasks over here. Now, if I want to build these kinds of text classifier, we cannot just build it as it is. So we generally follow a general pipeline. So the general pipeline for building the text classification system is something like this. It all starts with collection or creating the label data set for the given task. Then once we collect and once we create a label data set, next we will split the data set into two or sometimes three parts. Okay, so when I say two parts, it will be training and the test. Sometimes if I have large value of data, so instead of having train, we'll also have train and validation data. So this is how we will split the data set. And once we split the data, next we will transform the raw text into the feature vectors so that we can apply the machine learning models on top of this text data. Then we will perform the training of the classifier, that is the machine learning model, using the feature vectors that we have described earlier. And then while training, we'll make use of supervised machine learning approach. So we will make use of feature vectors as well as the corresponding labels from the training data set. Now, once the training is complete, we will check how exactly the model is performing with the help of evaluation metrics by applying on the model. Finally, once we have evaluated the model and once we are satisfied with the outcome, we'll go ahead and deploy the machine learning model. So we'll deploy the machine learning model and we are going to monitor its performance. So this is the overall pipeline whenever we are creating a text classifier. It starts with the text data, then we'll perform the split, we'll train it, we'll transform it, we'll evaluate it, and finally we'll deploy the model. And using the deployed model, we'll go ahead and generate the labels for the oncoming new text data. So this is the overall idea behind the pipeline for building the text classification system. Okay, now that you are aware of the general pipeline, let's go ahead and let's have a demo of a text classifier. So this is a website that we have got to help us understand the general idea of a text classifier. So I'll go to the site. Okay, so this is an example text classifier that we have got. So I'm going to mention something like this. So here, this describes the information about the text classifier. It says this classifier determines if a text is positive or a negative. It is well suited for short and long text, that is tweets, Facebook status, blog posts, product reviews, etc. And it has been trained on 2.8 million documents with data from Twitter, on product reviews and the movie reviews, and this can be used to conduct research and brand surveys and see the trends around the market campaign. So this is the overall idea about this example text classifier that we have got, and I'm going to write it like this. I'll say movie is amazing and I'll click on this button which says as classify. So here it says the positive is 0.97, that is 97%, and the negative is 3%. So overall, I can say that the given input text belongs to the positive sentiment, and this is what a text classification is all about. So for the given raw text, I want to assign the label, whether it is a positive or a negative. In that scenario, it's a sentiment analysis. If I'm assigning any categories, then it's a text classification in general. So this is the overall idea about this text classification. So with this, we come to the end of this video. As we proceed in the next video, we will look into the approaches to text classification. So I'll see you next time. Welcome back to your learning journey. Now in this video, let's look into the approaches to text classification in real-time projects. So whenever we are working on a real-time project, it is required that you want to build this service. Now the question is, how do you get started in a project perspective? Well, the easier way and the recommended way is to make use of already existing text classification service. So this is one of the easier way and a recommended way. The reason because this will help you to get a clear understanding as what this text classification service can do and what it cannot do, and it will help you to bring your idea to the action and test out whether it would really work for your business or not. And the another best part is by making use of the off-the-shelf models which is provided by Google Cloud Natural Language or Amazon Comprehend. So by using all their services, this would actually provide us the off-the-shelf content classification models. So using this off-the-shelf content classification models, we can clearly check how it is actually working. And with the off-the-shelf model, what is the performance that you're getting? And this can also be used as a baseline model and get an easy start for your business. You don't have to wait for 3 to 4 months for your data scientist to build a text classification model and deploy it into the production. You can just go ahead and plug and play those off-the-shelf models and use it to kickstart your business. And based on your requirement, you can either modify these services or you can build something on your own from scratch. Now let me just give you a quick demonstration about one of the text classification service that we have got. For the demonstration purpose, I'll make use of Amazon Comprehend. So Amazon Comprehend is one of the service that is provided by AWS. Let me take you to the dashboard or this first page of this Amazon Comprehend. So Amazon Comprehend, which is a natural language processing and text analytics service. So this is a service which uses the machine learning to find the insights and the relationships in the text. And some of the key features and the benefits of using this comprehend are, so it will help us to discover the meaning and the relationship in the text from the customer support incidents, product reviews, social media feeds, news articles, and all those things. So for example, we can actually identify the feature that's most often mentioned when the customers are actually happy or unhappy about the product. And the best part is we can train the model on our own data set, and we can identify the topics in the collection of text. So all these things can be done automatically, and the various use cases that you can use this comprehend are semantic search, voice of customer analytics, knowledge management and discovery, analyze and annotate the plain text or documents. So these are the various use cases of this Amazon comprehend. Now, in case if you want to get started, you can also refer to this API reference over here that is provided by AWS. By checking out this API reference, you'll get a clear idea what exactly that you can do, how you can integrate it with your already existing application. Okay, now to give you a demonstration, I'll click on this button which says as Launch Amazon Comprehend. So this will help me to launch this service. Here we can specify the analysis type, whether we want to use our built-in model or whether we want to use our custom model. So for the demonstration purpose, let's make use of the already existing model in AWS. So I'll ensure that the checkbox built-in is checked. Next, for the input data, they have mentioned some random input data. So I'll do one thing, I'll just remove this first input data and I'll keep only the second text. So the second paragraph clearly talks about the customer feedback. Here, customer feedback for Sunshine Spa, and here the send comments to Alice at sunspa@mail.com, and here it says the text review. I enjoyed visiting the spa. It was very comfortable, and but it was very expensive. Amenities were okay, but the service made the spa a great experience. So this is an example input text. Now, in case if you want to analyze this input text, an easier way is click on this analysis button. So now when I clicked on that analyze button, the text has been analyzed and now the entities have been extracted. So here the entities are nothing but the important elements which we have to focus when we are analyzing the text data. You will learn more about the entities in your future section when you're creating the chatbot for your own. For now, remember that entities are the important words which we want to focus. The entities that has been extracted are Sunshine Spa, which is the name of the organization, and 123 Main Street, which is a location. Alice is the name of the person. Okay. Sunspa@mail.com. This has been detected as other entity. Okay. And here we have the API call and API response for detection of the entities. So how the API request would look like and what will be the API response. Okay. And if I click on the key phrases, it will get me the important key phrases from this given text data, and click on the language. It will help me to detect what is the language that is being used in order to speak with the user, or in this scenario, the language used by the user. And sentiment, this will help me to understand what is the overall sentiment from the given text data. So all these things, yes, all these things have been done automatically with the help of this built-in service that is Amazon Comprehend. So this removes a lot of barriers for us. As an organization, when you want to implement this kind of text classification, it's a straightforward task. You just have to connect your text data to the available service and get the response and start getting the benefit of the amazing research done by Amazon. And as a real-time user, that is as a data scientist, you can also check out this service. This is provided by AWS for free. If you have a free tier account, then I highly recommend you to check out this service. So this is a demonstration of
text classification service. Now, apart from having the text classification service, we can also go ahead and build our own model. And using the trained model, we can include it in their service, or we can also create our own custom service depending on the project that we are working. So that approach is called as machine learning approach. So here in the machine learning approach, once we have the text data, we will apply the pre-processing. And once the pre-processing is completed, then we will apply the machine learning models to find the relationship between the text and the labels. Here, the machine learning models that can be used are Bayes model, logistic regression model, support vector machine, word embeddings. So we can use all this approach, or even we can also make use of deep learning based models, including the language model, which will help us to build our own custom model. So the general approach that we do is, to get started, we will make use of the base models that are available in those various services, and using that as a base model, using that as a reference, when we are creating a custom model, we will compare it with the existing model and see whether it is really worth it to have our custom model or improvise the already existing cloud service model. So it all depends on the maturity of the organization and the people and the overall maturity that is required by the business. So based on all these factors, the real world implementation approach will be decided. I hope this gave you a clear picture about the end-to-end pipeline and the way that we approach any text classification problem. Now, as we progress in the next video, I'll be showing you an end-to-end implementation of sentiment classification using the machine learning based approach. So I'll see you next time. So in this video, let's go ahead and perform the activity of sentiment classification. So here we'll be working with a data set which is called as a sentiment train data set. Now this is a data set which we have got from the kaggle.com. The original data was actually contributed by University of Michigan for building a classification model. Here we'll be classifying the sentiment for the given data set. Now this data set expresses the reviews by the users on various movies. Here, each comment is actually a record which is either classified as positive or a negative sentiment. So let's go ahead and load this data set. I've already downloaded this data set from the GitHub repository. In case if you want to load this data set, just use this URL that is present right here and paste it in your browser. Once you paste it in your browser, you'll be directed to the screen. Right click, select save page as. Now in this way, you'll be able to save this sentiment_train file. Okay, so this is how you can actually get started. And remember, this wget command works only on the Linux or the Apple MacBooks. Okay, if you're using the Google Colab, it would work, but if you're using the Windows system, it might not work. So be cautious about the same. Alright, so this is going to download the data for my Google Colab. So I recommend you to run the same in the Google Colab so that you can also work on it in an easier manner. So this is the data set, and this data set actually contains two columns. One is a text column. The other column is called as a sentiment. So the text column is actually the actual review comment on the movie, and the sentiment is a positive sentiment are actually labeled as 1 and the negative sentiments are actually labeled as 0. Okay, and this sentiment train data is separated by a tab character. Now with this understanding, let's go ahead and load this data as a data frame. So import pandas as pd, import numpy as np. Then I'm going to write it like this: train df is equal to pd.read_csv. Inside the parentheses, I'll specify the file name, that is sentiment_train, and here this delimiter, okay, delimiter is actually tab character. Okay, so this is how I'll read this data as a data frame, and I'll display first few entries of this data frame. So once I display first few entries of this data frame, this is how our data would look like. The positive sentiments is marked as 1 and the negative sentiments are marked as 0. Okay, now you can clearly observe over here, few of the text has been truncated. So this is mainly because of the column width. So in case if you want to modify the column width, we can also modify the same by setting up the option on the pandas library. So let me just give you a demonstration. Okay, so here this is truncated, right? So I'm going to write it as pd.set underscore option, and inside the parenthesis max call width, and I'll set it equal to 800. Okay, we'll set it as 800. That should be more than enough for us. Now I'll display first few entries. Now we should be able to visualize the complete text. Okay, so this has improved a bit, I would say. Now let's suppose if we want to get the summarization of the positive reviews, then what I can do is we can apply a filter something like this. I'll say train df. Okay, we will mention the sentiment equal to 1, and I'll send these values inside my indexing operator for my train df. So this will help me to summarize the first 5 positive sentiments. Okay, so let's see. So these are the first 5 positive sentiments. The Da Vinci book is awesome. This was the 5 Clive Cussler I have ever read. First Clive Cussler, but even books like Relic, and yeah, it's a positive review. I like the movie. So all these things are the reviews that we have got from this text data. We can also summarize the negative reviews as well by displaying first 5 negative reviews. So these are all the negative review text. Okay, so these are all the first 5 negative sentiments. So now that we have loaded the data set, we'll move on to the exploration of the data set. Okay, so let's do one thing. I'll stop the video over here. Let's continue with the exploration of the data set in the next video. In the last video, we have loaded the data set. Now let's go ahead and explore the data set. So exploring the data set is nothing but performing the EDA, that is exploratory data analysis. Here we can actually carry out this exploratory data analysis by counting the number of comments, positive comments, negative comments, and so on. For example, we can actually check how many reviews are actually available in this data set, and are the positive and the negative sentiments that we have got, whether they are well represented in this given data set or not. So we can actually get started with the EDA by calling the info method. See, by calling the info method, we can get to know the metadata of this data frame. So here it says that we've got 6918 rows in this given data set. And now if I want to perform the analysis about how many number of positive comments and the negative comments in this given data set, we can actually create a count plot. So let's go ahead and create a count plot. I'm going to write it like this: import matplotlib dot pyplot as plt. Then we'll also import the cbound library. Then let's define the figure region. Next, I'll just go ahead and create a count plot. So sns dot count plot, and I'll say my x is equal to my sentiment. Okay, and the data is actually my train df. Next, I'm going to perform some annotation. So here, in order to create the annotation, I'm going to write it like this: for p in ax dot patches. Okay, so we will mention as ax dot annotate, and here p dot get height, comma, I'll just mention it like this. So we have the plot over here. So we can clearly see that from the visualization, there are total of 6918 records. Now out of the 6918 feedback on the movies in this data set, 2975 records or 2975 rows belongs to the negative class or the negative sentiments, where the 3943 records or 3943 rows belongs to the positive sentiment. So overall, we can observe that there's a fairly equal representation in this data set. Now that we have performed the high-level EDA, let's go ahead and perform the pre-processing on this data set. So the next step is text pre-processing. Now here, in order to perform the pre-processing, so the core idea of this pre-processing is convert this unstructured data into a structured data so that we can efficiently work on this given data set. Okay, so the reason that we do this because I cannot use the unstructured data as it is. So we have to extract the features from the text data, and one way to do this is applying the bag of words approach. That is, each sentence, okay, each sentence that we have got is treated as the bag of words, and each sentence or the record is actually a document, and the collection of all documents is actually called as a corpus. Now with this understanding, let's apply this bag of words model. The first step in creating the bag of words model is to create a dictionary of all the words that is used in the corpus. Now at this point of time, we'll not worry about the grammar, and currently we'll only think about the occurrence of the word. Okay, then we will convert each document into the vector that represents the words that are available in the document. Now in order to do this, there are basically three ways which you have learned already. One, we can make use of count vector model. The other model is called as term frequency vector model. The third model is known as term frequency inverse document frequency model. So let's go ahead and implement the same. So let's start with count vector model. So here, when we talk about this count vector model, so let's consider two documents. Okay, I've got one document that says like this: I really like pizza. Okay, and there's another document that says like this. I'll say I never like pizza. So here, this is the given data set. So in the overall collection of these two documents is called as corpus, and I have two documents in this scenario. So the complete vocabulary is known as actually the dictionary. Okay, the complete vocabulary, which is also known as a dictionary, is containing of all the unique words that I have got in these two documents. So these words, you can say it something like this: I really like pizza, never. So these words will be my vocabulary words. And whenever I'm trying to represent these words into a numerical format, for each and every word that I have got, I'll be saying whether how many times it is present for my individual document. That is the overall idea behind this count vectorizer model. Okay, and the other approach that we have got is term frequency and inverse document frequency approach. Now in the term frequency inverse document frequency approach, what we do is we'll find the value of term frequency, and based on the value of term frequency, we'll multiply it with inverse document frequency, and based on that we will be generating the data into a numerical format. So that is the overall idea behind this technique. Okay, that's the overall idea behind this technique of count vectorizer and the term frequency and inverse document frequency technique. So let's go ahead and implement this count vectorizer. In order to implement this count vectorizer, so I'll start by importing the count vectorizer from the scikit-learn library. So from sklearn dot feature underscore extraction dot text, I'm going to import count vectorizer. Okay, once I import this count vectorizer, we'll initialize the count vectorizer. I'm going to write it like this: CV is equal to count vectorizer. Okay, then once we initialize this, so I'm going to generate the vocabulary. In order to generate the vocabulary, we'll just perform the fit on our training data set. So I'm going to write it like this: feature vector is equal to cv dot fit, and inside the parenthesis we'll specify our training data and select the column of text. Now once I perform the fit, next thing that we will do is we will extract the feature names. So the features are the individual columns that will be part of my count vectorizer is given by get feature names out. Okay, so in this way I'll get the list of features from the count vectorizer. Next, what we can do is I'm going to write it like this. Okay, so I'll mention as total length of vocabulary is, okay, so it is length of features and examples are, and then I'll just display some 5. Okay, I'll just display some 5 words from this vocabulary. See, the total number of unique words in the vocabulary is 2132, and some of the random features are 007, 10, 10 p.m., 12. So these are all the various words that has been identified for this vocabulary in this given data set. Okay, so we have created a vocabulary for this given data set. Now once we have created the vocabulary, we will have to transform this text data into a numerical format. The easier way to do this is by application of transform method. So let's go ahead and do that. I'll say train ds features. Okay, so let's call it as train data frame. Okay, train data frame features. We will say count vectorizer dot transform. We'll apply it on our data frame text column. Okay, now once I apply the transform, so we'll execute this. Okay, and if I simply display the train df features, see, this belongs to the type of sparse matrix. Now, why did it created as a sparse matrix, and what does it mean by sparse matrix? See, sparse matrix is a special type of matrix. It's a very special type of matrix where in this type of matrix, we will be generating the data with the help of an array. But the sparse matrix representation will be used when majority of entries are equal to 0. So in such scenarios, we will make use of this sparse matrix representation. Now in this scenario, the total number of unique words in my vocabulary is 2132. And if you look into to the individual sentence, I would basically have maximum, let's say 10 words in a sentence. Assuming the 10 words in a sentence, the remaining words on that vector of 2132 length will have it equal to 0. And if you consider the entire text corpus, then in such scenarios, like each and every row will have this kind of representation where majority of the values will be equal to 0. If I use the data as it is as a numpy array or the array representation, this is going to consume memory. This is going to consume a lot of memory, and to help us to store the data in an efficient manner, what scikit-learn does is it is going to generate whatever the outcome that I would get from the application of count vectorizer. It will be generated as a sparse matrix, which is an efficient way to store these kinds of values. And that is the reason when we created or when we try to display it, it is saying as it belongs to the sparse matrix. There are 6918 rows and 2132 features. Okay, that is what this data is actually telling us. Now, if I want to get, okay, if I want to get the number of non-zero values from this given data set, let me show you how we can do that. So I'll say get nnz. So the number of non-zero values that we have got is 65398. And if I want to give you an idea, see, in total, if I actually try to generate the data as a dense matrix, I will have the shape as 6918 by 2132. Okay, and there are a total of 65398 non-zero values. So just think about it, about the density of the matrix that we are dealing with. So the density of this matrix is 0.00434. See, that's the density. And if I multiply it with 100, okay, so the density of this matrix is actually very less. It is given by 0.4%. So this matrix has less than 1% non-zero values. That means more than 99% of the values are zero values. And that is the reason that we have made use of this sparse matrix representation. Okay, now for the visualization purpose, if I want to view how does this vectors would look like, I can just call the method of toDense. So this will convert the sparse matrix representation into a dense matrix representation. Okay, so we can visualize these count vectors in this format. So let's do one thing. Let's try to create this visualization. I'll write it like this. I'll say train df, okay, features 1, or we'll keep it like this, train df2. Okay, train df2, that's a variable name, and I'm going to call it like this, pd.data frame, and here I'll mention my train df features. Okay, I'll convert it to dense. Now once I've created into a dense format, the next thing that I'll do is I'll also say this columns is equal to features variable that we have extracted earlier. Okay, so this will help me to generate a data frame. And if I display first few entries of this data frame now, this is how the first few entries of this data frame would look like. Now to help us with the visualization, let me just pick up some random values based on my previous analysis. I'm going to write it like this, train df2 dot ilog. Okay, I'll just display the first row and I'll display the column values between 150 to 158. So if I execute this, so here under the word awesome, I have it as 1. See, under the word awesome, I have it as 1. So let's do one thing. I'll just write it like this. I'll get first two rows. Okay. For awesome, I have it as 1. So why am I having it as 1? So just observe our original data set. If you observe our original data set, and if I just display first two rows, in the first row, I have the word awesome. And because of that reason, under the word of awesome, I have it as 1. Okay, so all the other features or all the other words where it's not present, so that is having as 0. And we can also validate it by selecting the other columns as well. So let me just give you an example. I'll say train df2. Okay, and here I'll display some list of values. I'll say the, okay, the, then I'll say awesome, I'll say just, okay, so I will say book. Okay, I'll just display only these columns and I'll select, let's say, first two rows. See, based on the words that I've got in the text, I have the respective feature values filled. So this is the working of the count vectorizer. All right, team. So we'll stop the video over here. Let's continue with this analysis in the next video. I'll see you next time. So in the last video, we have applied the count vectorizer and we have seen the output of this count vectorizer. Now we'll go ahead and continue the pre-processing. So one thing that we could observe when we perform this pre-processing is it is considering each and every word in a given data set, that is each and every unique word. And the total unique words that we have got in this data set is given by the shape of this given data, that is 2132. There are 2132 number of features that we have got in this data set. So what it means is, let's say out of 6,900 rows, if I've got a specific word which is present in only in one sentence, even that is also considered as a valid feature. So that means we are currently having the scenario of having the low frequency words. And this is one of the key challenges whenever we are dealing with the data. So when the number of features become bigger and bigger, at that time, it will be very difficult for us to process those data in an efficient manner. So what we will do is, generally, we will remove those low frequency words. So what we can do right now is we can get the frequency of each feature or the word by taking the help of histogram chart. So I'll be writing the code something like this. Okay. So what I'll do is, this time I'm going to write it as feature underscore counts is equal to np.sum. Okay. We'll make use of this np.sum. Here I'll write it like this. I'll say train df underscore features. Okay, train df features dot to array. So this will convert it into the dense format. Then I'll say axis is equal to 0. I'll take the sum across the axis is equal to 0. So this will help me to get the total occurrence of each and every feature in this given data set. Next, I'm going to write it like this: feature count df is equal to pd.data frame, and here I'll create a dictionary. Okay, I'll create a dictionary of features is equal to features. Okay, then counts is equal to feature underscore counts. So this is how I'll be creating a dictionary. Now once this is done, we'll go ahead and create a histogram chart. So let me just define a figure region. pld.figure fig size is equal to 12,5. Okay, that's the figure region that I would use. And the next thing that I'm going to do is I'll say plt.hist, and here inside the parenthesis I'm going to write it like this: feature count df. Okay, and from here I'm going to access the column of counts, comma, bins is equal to 50, and we'll mention the range as 0 to 2000. That's the range that I would use right now. Then we will add the label as well. I'm going to say plt.x label. Here for the x label, it's actually the frequency of words, and for the y label, it is actually the density. Okay, so let's execute this. So this will help me to create a histogram chart. So this is how our histogram of frequently used words across the entire text corpus. Now what we can do is we can find the rare words. So to find the rare words in the dictionary, let's say the words that are present in at least one of the document, we can actually filter the features with the count equal to 1. So I can just do it like this. I'll say feature count df. Okay, so here I'm going to write it like this: feature df, and I'll say counts. So this will display the features where the count is equal to 1. So these are the features. So in total, we've got 1228 features which are present only once in this given data set. So these are present only once across all the documents in the given corpus. So these words we can actually ignore it. So we can actually restrict the number of features by setting the parameter of max features whenever we are creating the count vectorizer. So let's go ahead and apply the same. So for the ease of use, I'll just copy the code right now and I'll paste it over here. So we are initializing the count vectorizer, but this time I'm going to set the max features parameter is equal to 1000. Then we'll perform the fit on this given text data. Once we perform the fit, we will get the feature names. Then we are going to print the total number of words in the vocabulary, and we are just displaying few examples. Then let's go ahead and perform the transformation. I'll copy the code where we have done the transformation earlier. So this will help me to generate my train D of features. Okay. Now once I perform the transformation, let's go ahead and perform this feature count. So I'll copy this code. Okay, so I'll perform the feature counts, and once this is done, let's do one thing. I'll say feature count df. Okay, so we will sort the values on the basis of counts, and then we will sort it in a descending order. So I'll say ascending is equal to false, and we will call head. So let's look into the output, and from there we will get the clear picture. So I'm applying the count vectorizer with the maximum number of features that I will use as 1000. Then we will extract the feature names, that is the vocabulary. So the total length of my vocabulary now is 1000. Now that is amazing. Now once that is done, here the example vocabularies are this. Then we have applied the transformation on this given data. We have generated the overall counts, that is how it is actually appearing in this data set. Then we have created a data frame like this. Okay, now once I've created a data frame which counts the number of features, now this time I have displayed the words in my vocabulary in a descending order based on the number of occurrence. So from this output, we can observe that there are some features like the and. So all these words that we have got right now, so these are all actually the stop words which do not add any meaning to it. So I can say these words are irrelevant in determining the sentiment of the document. So what we can do is we can actually remove those stop words, which will help us in reducing the number of features further. So I'll stop the video over here, and let's see how we can remove those stop words in the next video. Now in the last video, we have seen that there are a lot of words which do not add meaning to the given sentences. So those words are called as stop words. So it's a good practice that we remove those stop words before we generate the features. The reason because if you have observed earlier, we are limiting the number of features that we want to have. Now when we are limiting the number of features, it will be a good practice if we remove those stop words and then perform the pre-processing. So let's go ahead and remove those stop words and work with it in an efficient manner. Now in order to remove the stop words, so what we can do is we can make use of the list of the stop words. Now to get the list of stop words, each and every library of natural language processing has its own inbuilt list. In this example, I'll be showing you as how we can make use of the inbuilt list that is provided by scikit-learn library and extend it with our own list and then proceed with the further activity. So let's go ahead and do that. First thing is, in case if you want to get the list of stop words, so I'm going to import it like this from sklearn dot feature underscore extraction dot text. I'm going to import English stop words. Okay, I'm going to import this English stop words as my stop words. So this is how I'll be doing the import. Okay, now once this is imported, if I open this my stop words, see this has been written for me, and this has been written in the format of a frozen set. So this has been written as a set for me. So this stop words contains the list of existing stop words, that is the default stop words as per the scikit-learn library. Now once the stop words are given, let's say if you want to extend this default set of stop words with our own custom set of stop words, then at that time we can extend this default list of stop words. So let's go ahead and do that. See, the reason that I want to do this activity, because if you observe our code, the words such as Harry, Potter, Vinci, the mountain, so code, so these are the words, okay, these are the words which are not part of the general stop words. If I display the general stop words, okay, just observe the list of general stop words which have been shared. See, this is the list of general stop words, okay, so amongst and another and so on. Now, apart from these default words, if I want to add my own domain specific stop words, we can also do that as well. So let's go ahead and do that activity this time. So if I want to add my own custom words to this list of stop words, I'm going to write it like this. I'll say my stop words is equal to my stop words dot union, and here I'm going to add my own domain specific words. Let's say Harry Potter, then code, then Vinci, mountain, movie, and movies. So these are the words that I'm going to add it right now as my custom stop words. Let's do one more thing. Let's validate Harry Potter, Vinci. Yeah, let's also add the word da. Okay, so now my stop words has the more words, that is the words according to my domain as well. In this scenario, the movie names. Okay, now once we have added our custom words as the stop words, next we can go ahead and use this stop words whenever we are applying the count vectorization. So for the benefit of understanding, I'm going to copy all these things. Yeah, I'll copy this cell itself where we are doing the count vectorization. Now here, while applying the count vectorization, I'm going to send in one more parameter that's called stop words is equal to my stop words. So benefit of doing like this is, here during the application of count vectorizer, before it gets the vocabulary, it is going to refer to the stop words, that is my list of stop words, and removes those words from the vocabulary and then decide the 1000 top features from the given data set. Okay, that's the best part of applying this stop words for this count vectorizer. Now, once that is done, let's go ahead and generate the output. So we have done the count vectorization, we have extracted the feature values, and we have looked into the total number of times that each and every feature is present. And at the end, if we now display, so we now have Harry Potter, code, Da Vinci. So we still have those values. Let's revalidate it and let's remove those as well. So once we have applied this activity, so we can now see that, see the previous words that we had, that is the Harry Potter. So all those words have been removed, and this is how the current output would look like. So we have taken care of the stop words, and after we have taken care of the stop words, so this is how the overall features would look like. Now, interestingly, we see the other problem. The other problem is, here we have got the word love and we have the word like, and we also have the word awesome. So all these words is actually conveying the positiveness of the movie. So instead of using multiple words which conveys the same meaning, as a practice, what we can do is we can convert those words into a root word which will help us to reduce the feature. So that's the next step that we'll be doing right now. And this activity of converting the word to the root words is called as stemming and lemmatization. And here, when we talk about stemming, so stemming is all about converting the word to its root form or the base form, where that root form may not be available in the dictionary. Now, when it comes to lemmatization, lemmatization is converting the word to the root form, but that root form word is available in the dictionary or in this specific language dictionary. So, in order to do this activity, we've got various libraries. We've got NLTK library, we've got Spacey library, and each and every library has the option for us to get the lemmatized word or the lemmatized version as well. Now here, as part of demonstration, we'll be making use of the NLTK library. So let's go ahead and apply the stemming and lemmatization so that we can convert the word to its base form. Okay, so let's go ahead and do that activity. So I'll begin by writing like this. From nltk.stem, we'll be importing the porter stemmer. Now once the porter stemmer has been imported, let me create an object for the porter stemmer. Then here I'm going to create my count vectorizer analyzer. So I'll write it like this: analyzer is equal to dot build analyzer. Okay, now once this is done, I'm going to create a custom function for stemming and the stop words removal. So I'm going to write it like this. I'll say def stem underscore words, and this will take an individual document. And here what I'm going to do is I'm going to create Python list like this. I'll say stemmed words is equal to stemmer dot stem, and here for w in analyzer doc. Okay, now once this is done, that is once the list comprehension is done, we are going to remove these stop words. So I'll write it like this. I'll say non-stop words is equal to, I'm going to write it like this, for word in stemmed underscore words. Okay, so for word in stemmed underscore words, if not in my stop words, then only I'll consider that as a valid word. And finally, I'm going to return the non-stop words. So this is how I have created a function. Now, once this function has been created, if I want to include it, so let's fix the same. If not in, okay, I'm now modified the code over here. So what I'm doing is I'm taking the set difference between my stem words and the stop words. Okay, this will help me in returning the every element that I have got right here, that is my non-stop words. Okay, now once this is done, we'll just go ahead and create a count vectorizer. So I'll say count vectorizer and max features as 1000. Now since we are taking care of both stemming and lemmatization, I'm going to mention my analyzer is equal to stem underscore words. Okay, we'll perform the fit on our training data set, then apply the count vectorizer, and after the application of count vectorizer, we'll create a data frame. So this is how the overall output would look like. Let's wait for it to complete the execution. See, we have now removed the stop words and we have performed the activity of stemming as well. So we have converted the words to its base form. Once we have converted the words to its base form, so this is how the overall data would look like. So the overall vocabulary looks, at least we have done the pre-processing, it looks much better compared to what we have seen earlier. Now that we have seen how to perform this stemming, so similarly, in case if you want to replace this stemming with lemmatization, what you can do is instead of creating analyzer with stemming, you create analyzer function. You create a function for wordnet lemmatizer and apply the lemmatization. So that's one way that you can apply this activity. All right, team. So once this is done, we can go ahead and take the next step to look into the distribution of words across the various sentiments. So by understanding that, you'll get a better idea as how each words are being used. All right. So we'll stop the video over here and we'll continue in the next video. So let's continue to work with this data set, and now let's look into the distribution of words across various sentiments. Here, the reason that we want to do this activity because we just want to understand how each of the words are being used. Let me just give you an example. If I find the word as love, so is it conveying the positive sentiment or is it conveying the negative sentiment? And if I come across the word as suck, does it coming in the sentiments which is the positive sentiment or the negative sentiment? So that's the key kind of analysis that I'm trying to perform right now. So let's go ahead and do this activity. So in order to look into this, I'll just create a data that will look like this. I'm going to write it like this. I'll say train df3 is equal to pt dot data frame. Okay, and here I'm going to mention like this. I'll say train df features, that's my previous data frame, dot to dense. And once I convert it into the dense format, then next thing that I'll do is I'm going to assign the columns as the features. Okay, now once this activity is done, okay, once I create this data frame of train df3, next what I'm going to do is I'm going to assign the sentiment label to this data frame. So I'm going to say train df3 sentiment is equal to df sentiment. Okay, now I've done this activity. Now let's go ahead and let's create a bar plot to get a complete understanding about our data set. I'll say sns dot bar plot, and inside the parenthesis my x as the sentiment. Okay, and for the y I'm going to mention it as suck. My data is equal to train. Okay, so then here while performing the estimation, I'll mention my estimator as sum. So finally I'll say plt.show. So let's execute this. So this time when I execute this, see, this is how the overall output would look like. So if I have the word suck, then it appears mostly in the negative sentiment. Okay, and if I use the stemmed version of word awesome, that is AWESOM, so what it means is the word awesome is present mostly in positive sentiment document. And let's do one thing, let's think about the neutral word. So let me pick up a neutral word like really. Okay, there's a word called really. Okay, so let's see how does this like neutral word would look like. If I look into the data distribution of really, so which is a stemmed version of really, so you can clearly observe that this is a neutral word and this is coming in both positive and the negative sentiments. So let's look into the word hate. Okay, I'm going to say y is equal to hate. So for the word hate, so this is mostly coming in the negative sentiment. So this absolutely makes sense, isn't it, guys? So the positive sentiment words are appearing in the positive sentiment classified documents, and negative sentiment words are appearing in negative sentiment classified documents. So that's a good thing. So this gives us a better way of representation of the data set at least. So now moving ahead, let's go ahead and implement the model. So the model that we are going to use this time is the Naive model. So this is the common machine learning model that we generally use it for text classification. So the reason is, as per the various research, this natural language processing task works better with the Naive model in a much better way. So that's the overall reason. So here, when we talk about the Naive model, So the way this is going to work is this works on the basis of conditional probability. Okay, this works on the basis of conditional probability. So probability of a given word. So if I have got a specific word, I'm interested in finding the overall probability as, okay, if I have the word of hate, so what is the probability that it belongs to a negative sentiment? And if I have the word really, what is the probability that it will belong to a positive sentiment or a negative sentiment? So to give you a clear perspective and a high level intuition behind this Naive model, so let's consider this example. Let's say we have got the word hate. So here, this Naive model works on the basis of conditional probability. The conditional probability is given by probability of occurrence of event A given event B is equal to probability of occurrence of A and B together divided by probability of B. Okay, now this is the formula of conditional probability. Now here the probability of B given A is given by probability of B intersection A, that is B and A occurring together, divided by probability of A. Suppose if I call this as equation 1 and I'll call this as equation number 2, what I can do is I'll modify this equation number 2 and I'm going to write it like this. So probability of B intersection A can also be written as probability of A intersection B because they both would mean the same thing. So I can now modify my equation 2 as probability of A intersection B is equal to probability of B in given A multiplied with probability of A. And I'll call this as equation number 3. So what I'll do is I'll substitute 3, okay, I'll substitute 3 1. So what it means is in place of this A intersection B, I'll substitute this equation number 3. So probability of A given B is equal to this time probability of B given A multiplied with probability of A divided by probability of B. So this is the equation of Naive equation. Okay, this is the Naive equation. Now what it means is if I have got a specific word in my document, I'm trying to understand what is the probability that whether that document will be a positive sentiment or a negative sentiment. So if I want to give you an idea, what it means is probability of document being positive given the word is awesome. So I'll go ahead and find this probability. So if I have the word awesome, what is the probability that the document will be positive? And if I have the word awesome, what is the probability that my document will be the negative one? So I'll do these kind of analysis, and based on this analysis for each and every word that I've got in my document, at the end, the overall probability I'll get, what is the overall probability of document being positive and the negative. Whichever is the one which is having the highest probability, that's the overall sentiment that I'll be assigning for my individual document. Okay, so this is the overall idea about this Naive theorem. Now, when we are working on this Naive theorem or the Naive classifier, here there are various types of models. One is the Bernoulli-Naive model, and two, there is like multinomial Naive. So, like this, there are various types of Naive model. Now, in our scenario, since we are working with the count vectorizer, the suggested Naive model that we'll be using is the Bernoulli's Naive model. So let's go ahead and implement this Bernoulli's Naive model on this given data set so that we can perform the activity of classification. So first I'll start by splitting the data set from dot model underscore selection. We'll import train test split function. Then we'll split the data set into two parts. So xtrain xtest, ytrain ytest is equal to train test split, and inside the parenthesis it is df features. Okay, that's my x, and for the output it is train df dot sentiment. Okay, so this is my output. Let's just validate it whether we are referring correctly or not. Okay, so let's do one thing. So train df features contains my training features. Yes, I think this is looking correct. Yeah, and train. Okay, next here I'll specify my test size as 0.3 and random state is equal to 42 to ensure the repeatability of the split. Now once we split the data into two parts, then we'll initialize the model from sklearn dot naive underscore base. I'm going to import Bernoulli NB. Then I'm going to say that Bernoulli is equal to, and here I'll perform fit on my training data set, Bernoulli dot fit, and I'm going to say xtrain comma ytrain. Once we perform the fit on this given data set, we can go ahead and generate the prediction. I'll say ypred is equal to Bernoulli dot predict, and we will specify our x test. So what we have done is we have performed the fit on this given data set and we have generated the prediction on the test data. Now let's go ahead and perform the evaluation on the given test data. So to perform the evaluation, we'll make use of various metrics. So from sklearn dot metrics, I'm going to import the classification report. So I'll say classification report, and inside the parenthesis I'll specify my ytest comma ypred. And if I execute this, so this is the overall output that we would get. So let's send it inside the print function. So this is the overall output that we get on this given data set. So we've got the F1 score of closer to 98%. That's amazing. And the accuracy is also 98%, which is pretty good for this given data set. Let's go ahead and create a confusion matrix. So here I'm going to write it like this. I'll also import my confusion matrix. So I'll say CM is equal to confusion matrix, and I'll specify my ytest comma ypred. Then we will say sns dot heat map, and inside the parenthesis, so it is confusion matrix and not is equal to true. Okay, so this is going to create a heat map for this confusion matrix. This is how it would look like. Let's fix the format team. So I'm going to say format is equal to dot to f. So this will be much better when it comes to interpretation. So this is how the overall output would look like. So in the confusion matrix, the rows represents the actual number of positive and the negative documents in the data set, and the columns represent the what model has actually predicted. The label 1 means positive sentiment and the label 0 means negative sentiment. The overall figure shows that as per the model prediction, there are only 14 positive sentiment documents which are classified incorrectly, and there are 28 documents which are classified in wrongly as positive sentiment, even though it belongs to the negative sentiment. Okay, so in this scenario, the 14 is my false negative and 28 is my false positive, and rest everything have been classified correctly on this test data set. Alright team, so with this we come to the end of this video. Now in the next video, let's continue with the implementation and let's see what is the overall performance that we would get if we implement the TF-IDF technique. So I'll see you next time. Now in this video, let's go ahead and implement the classifier using the TF-IDF vectorizer. Now till now we have made use of this count vectorizer. Now while working with this TF-IDF vectorizer, we've got the option. So the option is we can either make use of TF-IDF vectorizer, or we can simply make use of this vectorizer version. Now to control the same, we've got the parameter that's called as use underscore IDF. By default it is set as true. We can also set it as false in case if we want to make use of term frequentizer only. Okay, so we can use it to create the term frequency inverse document frequency. So let's go ahead and implement this TF-IDF vectorizer for the given data set. I'll start by importing it this time. So from sklearn dot feature extraction dot text, I'm going to import TF-IDF vectorizer. Okay. Next, I'm going to write it like this: TF-IDF is equal to TF-IDF vectorizer. And I'm going to mention my analyzer is equal to stemmed words, which is what the function that we have created earlier. And then I'm going to mention my max features is equal to 1000. So I'll initialize my TF-IDF vectorizer. So let's validate. It's actually stem words. Now once this is initialized, we'll go ahead and perform the fit. So TF-IDF, I'll use it in the same cell, TF-IDF dot fit, and I'll apply it on my train DF text column. Okay, so I'll apply the fit on this train DF column, and I'll say feature vector is equal to, I'll assign the output of this fit. Then what I'll do is I'll get the features. So train DF features is equal to TF-IDF dot transform. I'll apply this transform on my train DF text. Okay. Now once this is done, we can get the feature names. I'll say features is equal to feature vector dot get feature names out. Okay, this is how I'll be generating the features as well as the vocabulary. Okay, now once this is done, we can go ahead and apply it on the machine learning model. So this time, since we have got the values, that feature values in the real number, that is the continuous values format, so the model that we can use is the Gaussian I-Bayes model. So the Gaussian I-Bayes model is generally used for the continuous variable, and it assumes that the data is distributed in the format of Gaussian distribution. So let's go ahead and implement this Gaussian NB. So from sklearn dot naive Bayes, I'm going to import Gaussian NB. Okay. Next, we'll split this given data set. So I'll just copy this code and I'll paste it right here. Okay, so we'll split the data set in the same format. Next, once we have split the data set, I'm going to initialize my model. So Gaussian NB. Then we are going to perform the fit on this given data set, xtrain comma ytrain. Then we'll go ahead and generate the prediction. Ypred is equal to Gaussian dot predict, and I'll apply the prediction on the test data. Then we'll print the classification report. So for that, I'll just copy paste my previous code over here. So this is how the output of this classification report would look like. Okay, so currently it is expecting the array as a dense format. So let's just go ahead and do that. So this is how the overall output would look like. So we can observe that the precision and recall seem to be much the same. So this is the overall output that we would see. So in this scenario, the accuracy is pretty much high because the data set that we are working is clean, and we have actually curated this data set so that we can get the better accuracy. Now, while working on the real world data set, obviously this may not be the scenario. So you'll come across a lot of challenges. You'll ensure that you'll apply all the pre-processing and then ensure that you are able to get the better accuracy on the given data set. All right. So with this, we come to the end of this video. Now in the next video, we'll talk about the challenges that we will have while working with the text classification. And we'll also look into the other approach that is known as bag of uh, bag of words approach, but with the help of n-grams. So I'll see you next time. So let's talk about the challenges in text analysis. See, whenever we are working with the text data can be highly content specific or the context specific. The language the people use to describe the movies may not be the same for other products, let's say the food products or let's say apparels. So whenever you're working with the data set, the training data needs to come from the similar context, that is the similar distribution of the data whenever you are building the model. And the language may be highly informal. The language the people use on the social media may be a mix of languages as well as the emoticons as well. So it's very important that you keep that idea as well whenever you are working with the data set. And the training data also needs to contain the similar examples for learning purpose. Now, while working, when we make use of this bag of words approach, the bag of words model completely ignores the current structure of the sentence or the sequence of words that are present in a given sentence. Now we can overcome this by some extent by making use of n-grams. So let's see how we can make use of the n-grams approach. So we will make use of n-grams. Now what exactly is this n-grams? So here, when we talk about n-grams, we'll be considering the multiple words which are present in a sequence. The model that we have actually built in this chapter created features out of each token or word. But the meaning of some of the words might be dependent on the words it precedes or it succeeds. So, for example, if I've got a word as happy, and if this happy is actually preceded by a word called not happy, then it is actually conveying the negative emotion and not the positive emotion when we look into the individual word. So, it should be considered as one feature instead of two features. So this n-gram, that is the n consecutive words gram, is a contiguous sequence of n words. So when two consecutive words are treated as one feature, we generally call it as bigram. And if three consecutive words, then it's called as trigram, and so on and so forth. So what we will do is we are going to write a new custom analyzer, that is get stemmed tokens, which is going to split these sentences and stems the word from them before it creates the n-gram. So let me just go ahead and show you the overall implementation of the same. So I'm going to write it like this: from nltk dot stem, I'm going to import the porter stemmer. I think we have already imported, but let me just show you, and I'll also import the regular expression. I'm going to initialize my stemmer. Now once this is initialized, I'm going to create a function. So def get stemmed tokens, and here this is going to get an initial document. Then inside this function, I'm going to first perform the tokenization. So all tokens is equal to for word in nltk dot word underscore tokenize, and this will get my individual document. And for the tokenized words, I'll just keep it as my individual word. So this will help me to perform the list comprehension. And then what I'm going to do is I'm going to remove the characters which are other than alphabets. So in order to do this, I'm going to get the clean text, which is a blank Python list. Okay. Once I create this blank Python list as clean text, I'm going to write it like this: for each token in all underscore tokens. Okay. Then I'm going to write it like this: if re.search, and inside the parenthesis, I'll just mention the rules for the regular expression. So A to Z, comma, I'll mention my each token. Okay, so I'll mention the pattern in this way. Then, okay, for each output that I'll get right here, text, I'm going to write it like this: clean text. Okay, clean text, and this is followed by append, and I'm going to write it as each underscore token. Okay, this is how I'll do the activity. So let's just fix this regular expression. Yeah, now it is looking good. Okay, now once this is done, we'll go ahead and perform the stemming. I'll say stem token is equal to, so for T in clean text, okay, for each of the token that is present in my clean text, what I'll do is I'm going to apply the stemmer, that is stemmer.stem. I'll apply the stemming on my individual token, that is T. And finally, I'm going to return the stem token. So this is how I'll be creating the function that is getStem tokens. I'll perform the tokenization and then I'll go ahead and apply the regular expression. Finally, I'll perform the stemming. Now, when I'm using the TF-IDF, this TF-IDF vectorizer will use the current method that we have described, that is getStemmed words. And along with that, this time I'm going to mention the n-gram range parameter, which is actually a tuple value for creating the n-grams. For example, if I mention something as 1, 3 for the parameter, then it would mean that start with one word with two words as well as three words. So two words as well as three consecutive words will also be considered as the features. So let me just copy the previous code and I'll paste it right here. So we are importing the TF-IDF vectorizer, and for the analyzer, I'll be making use of getStemmed tokens. Okay, and this is actually my tokenizer. Okay, this will be my tokenizer since we are just performing the tokenization right here. Okay, and this tokenizer will take care of both stemming as well as the tokenization activity. Then we will specify the maximum features. Let's keep it as 700 for the demonstration purpose. I'm going to mention my stop words as the English. Okay, or else we can also make use of the previous stop words as well. Let's use the same. So my stop words. Okay, and more importantly, the n-gram range, I'll just mention it as 1, 2, 3. Or let's consider only bigrams since we are using only 700 features. Okay, you can also test out with your own values. Then we are applying the fit on the data set, performing the transformation, and then getting the feature values. Now once this is done, we'll just go ahead and build the model since this is TF-IDF vectorizer. Okay, so we'll have to do the same. So here, okay, let's fix that. Currently word tokenizer is not available. Let's just fix the same. So here this is actually available inside the NLTK dot tokenize dot word tokenizer. I think now this should work. Okay, the code is now being fixed. Okay, once it has been fixed, so here it's asking me for some download. So let's just complete the same and you'll be able to see the overall output. Perfect. So what we have done is we have done some few mistakes while typing the code. So instead of doc, I had mentioned as instead of document, I had mentioned as doc, and then this word tokenize is actually available inside nltk.tokenize.word underscore tokenize. Now once this is done, we have performed the TF-IDF vectorizer. Next, we are performing the fit with the help of Gaussian Bayes model and generating the classification report. So this is how the overall output would look like. Okay, so this is how the overall output would look like, and it is looking much good, isn't it, guys? So what we have done is we have made use of Gaussian Bayes model and applied this activity of fitting the model using the n-grams. So by completing this hands-on activity, I hope you're now confident and familiar as how do we actually perform the classification task whenever we have got the given data set. Now here we have made use of a direct approach. Okay, we have made use of a direct approach where the direct approach is getting the data
And once the data has been received, so we have performed the pre-processing and we have generated the feature vectors using the count vectorizer and the term frequency inverse document frequency vectorizer technique, and perform the fit or the evaluated the model. Now, apart from this, you can also take another step by getting the word embedding. So you can also generate the word embedding and make use of already created word embeddings and perform the classification on this given data set. So we'll touch base on the word embeddings in the future section when we talk about the chatbot and when we talk about the sentiment classification. There we will work on this activity again, but I'm just giving you a hint that you can also try out now as well. So with this, we come to the end of this section. So I look forward to seeing you next time. So take care, everyone.